The outer planets, Jupiter, Saturn, Uranus, and Neptune, share numerous characteristics and are often collectively termed the Jovian planets, named after their most prominent representatives. The giant planets, or gas giants, are distinct from Earth and the other terrestrial planets of the inner solar system, representing the largest celestial bodies we can examine closely, aside from the Sun. Jupiter is so immense that it has often been regarded as a nascent star, a perception it partially justifies. Its composition mirrors this. Akin to the Sun, it preserves all the gases and a portion of the heat from its formation. Its composition comprises approximately 90% hydrogen and 10% helium, mirroring the cosmic abundances of the primordial universe following the Big Bang. The other Jovian planets possess analogous proportions of these primordial elements. We will allocate additional time later to examine Jupiter's composition and delineate the exact formula for constructing a gas giant planet. Jupiter and the other planets, including Earth, coalesced with the solar system approximately 4.6 billion years ago, a process that has long been one of science's most enigmatic and intriguing mysteries. Following numerous false beginnings, despite ongoing discussions regarding certain specifics, we now possess a reasonably comprehensive understanding of the events that transpired. All cultures possess origin myths. We bypass them here and commence with the nebular hypothesis Immanuel Kant and Pierre-Simon Laplace proposed in the late 18th century. Kant was a German philosopher, while Laplace was a French mathematician. They independently attempted to elucidate the evolution of our system's planets to orbit directly, anti-clockwise from a northern perspective of the Earth's ecliptic, and in approximately the same plane. They posited that the Sun and planets originated from a swirling nebulous cloud that underwent gravitational contraction. The central mass collapsed inward, generating heat sufficient to emit its own light, while the remaining cloud flattened into a disk. Aggregates of matter in the disk subsequently coalesced to form the planets and their moons. The Kant-Laplace model posits that the nebula's initial rotational motion determines the trajectory of the planet's orbits. While the nebular hypothesis proposed by Kant and Laplace was highly credible, a significant obstacle persisted for an extended period: angular momentum. In summary, while most of the solar system's mass is concentrated in the slowly rotating Sun, the predominant angular momentum is found in the planets. Due to the inability to elucidate this asymmetry within the framework of the Kant-Laplace model, an alternative hypothesis emerged, positing that the planets originated as byproducts of a rare grazing interaction between another star and the Sun during the Sun's formative stages as a stellar body. Most astronomers preferred the grazing encounter theory at the onset of the 20th century. In 1909, American astronomer Percival Lowell, who founded an observatory in Flagstaff, Arizona, to investigate Mars and subsequently broadened his research to include other planets, proposed that the numerous spiral nebulae appearing in deep sky photographs could represent nascent solar systems in formation, characterized by the interaction of a dark star and a luminous star. Consequently, millions of solar systems may be dispersed throughout the cosmos. Lowell posited that if a stranger nears a celestial body sufficiently, it will invariably induce tidal forces on the latter's mass, and if the proximity is exceedingly close, these tidal forces will be substantial enough to disintegrate the body along the axis of their influence. Consequently, segments of the body will be detached from the principal mass in two antipodal directions. This is exactly what is observed in the spiral nebula. Furthermore, no known action would similarly address the body. As the stranger moved on, his influence waned until his allure no longer outweighed that of the body due to its fragmented state. It is feasible to manipulate and compel these to traverse elliptical orbits around their initial mass. Upon the formation of a solar system, the knots within the nebula would give rise to planets. Ironically, it was Lowell's assistant, Vesto Melvin Slipher, an Indiana University alumnus employed by Lowell in 1901, to oversee a new spectrograph aimed at validating Lowell's disputed theories regarding Venus's rotation, which ultimately demonstrated the unfounded nature of Lowell's conjectures. Rather than validating Lowell's and others' conjectures regarding spiral nebulae as developing solar systems, Slipher determined that they were predominantly moving away from us at significant velocities. This ultimately led astronomers to acknowledge that spiral nebulae are significantly more important than forming solar systems. They are galaxies, immense aggregations of stars, participating in the overall expansion of the universe. As the expanding universe gained recognition, the close encounter theory of planets was concurrently declining. During a close proximity event, the delicate filaments of the Sun would have been too insubstantial to coalesce into planets. The nebula hypothesis resurges. By the 1940s and 1950s, the nebula hypothesis regained prominence as astronomers elucidated methods by which Kant and Laplace validated it, exemplified by a false color image of a protoplanetary disk forming around the star Beta Pictoris, observable from latitude south of Hawaii. 1984, Bradford A. Smith of the University of Arizona discovered the disk. Bradford A. Smith, who collaborated with Clyde Tombaugh's Planetary Patrol early in his career, participated in a program conducted at New Mexico State University to systematically photograph the planets. Smith assumed the role of imaging team leader for the Voyager spacecraft missions to the outer planets, encompassing flybys of Jupiter in 1979 and 1980. Following the 1989 Voyager 2 flyby of Neptune, he conducted observations that revealed the presence of a protoplanetary disk surrounding the southern hemisphere star Beta Pictoris. In 2016, he posed with the 33 cine-primed Abbott Lawrence Lowell astrograph, which his mentor Clyde Tombaugh used to discover Pluto in 1930. A substantial amount is now understood regarding the drama of the solar system's origin, with Jupiter consistently occupying the principal role following the Sun. Approximately 4.6 billion years ago, the Sun and planets originated from frigid, dark interstellar molecular clouds. The initial documentation of these clouds occurred in the wide-angle photographs of the Milky Way captured by the esteemed American astronomer Edward Emerson Barnard around the early 20th century. They were later studied by and named for the Dutch-born astronomer Bart Bok, who personally thought they should be called Barnard globules. We see them silhouetted against the background stars and look from our position on one of the galaxy's spiral arms toward the center of the Milky Way. These clouds are very cold, with typical temperatures of around 10 Kelvin, 10 degrees above absolute cold, and densities of several thousand molecules per cubic centimeter. If a dark cloud is dense enough, or if it happens to be suddenly compressed by passage through the dusty arms of the Milky Way or by a supernova blast in its proximity, it begins to collapse in on itself. At first, this collapsing tendency is resisted by magnetic fields, but eventually the magnetic fields leak out of the cloud. Once this stage is reached, collapse begins in earnest, and the gravitational energy of collapse is converted into heat. However, because of the cloud's low temperature and low density, it remains transparent to radiation at first. The radiation escapes into cold space. The collapse at this stage is said to be isothermic. That is, it occurs without warming the cloud. During this isothermic collapse phase, the cloud undergoes fragmentation into hundreds of subclouds, each massive enough to contract further in its own right. These substars, or protostars, continue to contract until they have become stellar-sized. Stars are what they are destined to become. Though most of the cloud's material falls directly into the incipient star and adds its mass, some leftover remnants are spun into a disk of the kind Kant and Laplace envisaged long ago. The swirling cloud of gas and dust out of whose broken rings planets form derives its symmetry from the same cause as the spiral form of the galaxy itself. It is the symmetry of matter in rotation. The gathering together of matter realized on a grand scale in the starburst of the galaxy is small in the solar system's formation. As the subclouds contract, they rotate faster and faster, like a skater speeding up by pulling her extended arms inwards against her chest. Over time, the swirling material reaches supersonic speeds. The centrifugal force causes material in the cloud to flatten toward the outside, until the cloud's shape resembles that of a barred spiral galaxy. At this point, it has formed a circumstellar disk, like that has been imaged around Beta Pictoris. The rapid rotation leads to further fragmentation of the cloud, with most of the angular momentum of rotation becoming stored in the relative motion of the largest fragments. These fragments will form the stellar components of binary or multiple star systems. Uncompanioned stars, such as the Sun, are much less common. Incidentally, there is nothing to prevent binary stars from having their own planetary retinues. As we now know, most do. As the contracting cloud grows more and more dense, it finally reaches the point where it becomes opaque to radiation. No longer able to escape into space, the gravitational energy released as the cloud continues to collapse rapidly warms its womb-like interior. As it does so, there is a corresponding buildup of gas pressure resisting further contraction. The opposing forces, gravity inwards, gas pressure outwards, eventually reach a delicately crafted compromise as the gravitational energy of collapse comes into precise balance with the heat energy of expansion. A wonder of nature appears in its basic structure, which is elegant and simple, but intricate in detail. A star is born. At first, the star is a stellar pupa tucked away inside its gas and dust cocoon, glowing with a softly beating irregular light. It is then known as a T Tauri star, after its prototypical namesake in the constellation Taurus. Such a star has strong emission lines in the spectrum and a rapidly varying output of infrared, optical, and ultraviolet radiation. Still surrounded by a gas and dust disk, such a star undergoes periodic outbursts, each lasting about 100 years, in which mass is transferred from the disk onto the young star, increasing its luminosity. The gaseous component of the disk lasts only about 1 to 10 million years against the ravages of these periodic outbursts. However, it takes tens of millions of years, in the case of a one solar mass star, about 40 million, for the star to settle into an even-tempered luminary that will burn steadily and predictably for billions of years on the band of stars, graphed according to mass and brightness, that astronomers refer to as the main sequence. This means that by the time the star forsakes its turbulent youth and sets out as a stellar debutante on the cosmic stage, it has already begun to form a retinue of planets, or at least of gas giant planets, such as Jupiter and Saturn. Calculations show that these giant planets must have formed within only the first 1 to 10 million years after the Sun, before the gas, hydrogen and helium formed in the Big Bang and the chief components of the solar nebula, was dispersed into interstellar space. There are two competing theories regarding the formation of Jupiter and the other giant planets. The first assumes a top-down process, in which Jupiter formed through the rapid and direct collapse of a cold, dense gas and dust clump in the circumstellar disk's outer part. Because the collapse occurs so rapidly, an enormous amount of heat would be trapped deep within the planet. The second theory assumes a bottom-up process, the so-called core accretion model. Here, planet-sized ice and rock cores form first and grow rapidly through an influx of gas and dust. A few objects, by a fundamentally random and unpredictable process, sometimes called a Monte Carlo process, decisively outgrow the rest and become the most massive and dominant objects in the solar system, after only the Sun itself. This process is more gradual than that involved in a rapid and direct collapse, and the interior of the planet produced would be relatively cooler than in the top-down model, though still red-hot. In principle, it should be possible to decide between these theories by observing infrared radiation from giant planets belonging to other stars, which are only hundreds of millions of years old. These planets have not yet had time to cool, as Jupiter and Saturn did long ago, and so should disclose the manner of their formation. Investigations along these lines are now in progress. This is one avenue of approach. Another, much closer to home, is to observe Jupiter itself from an orbiting spacecraft. As we shall see later, instruments on board the Juno spacecraft gather data to provide definitive answers regarding how Jupiter formed and evolved. After its formation, Jupiter would have been hard to destroy and unaffected by the young Sun's energetic outbursts. Youthful as it appears, with violent and tempestuous changes in its colorful clouds, it is a very old world. At almost 4.6 billion years old, it is nearly as ancient as the Sun itself. First among unequals. Other cores, embryonic planets, formed simultaneously with the one that formed Jupiter. The latter just happened to be situated in the right place at the right time to swell to unusually gargantuan proportions. Growing a giant planet from the bottom up is described in the title of a recent technical article, Growing Gas Giant Planets by the Gradual Accumulation of Pebbles. That title conveys an astounding thought. The pebbles were primordial centimeter to meter-sized objects swirling in the protoplanetary disk, and out of these seeds, a gas giant planet would form and grow to have a mass 318 times that of the Earth. Only sweeping out all the gas along its orbit prevented it from growing. There was effectively no more substance left to add to its bulk. According to a proverb, variously expressed, "From small beginnings grow enormous things." It was certainly so in the early solar system. What played out was akin to a giant game of Monopoly, in which the game board was on the solar system's scale, and where the laissez-faire competition was not for money or land holdings, but mass. Meanwhile, a variation of the same theme played out in the inner solar system, which was largely depleted of gas early on. There, bits and pieces of rocky debris formed the smallish lumps of the terrestrial planets, including Earth. From the outset, the basic scheme of the solar system was established, each world being defined by the circumstances of its birth. Small rocky planets inwards, giant gaseous planets outwards from the Sun. Our own position is close to the hearth. Compared to our gigantic brethren, we, with the other terrestrial planets, are little more than moths circling the flame. Gravity's grave effects. All the planets revolve around the Sun in roughly the same plane, the ecliptic, because ancient observers noted that eclipses of the Sun and the Moon occurred exclusively in this plane. The direction of motion in their orbits is anti-clockwise as viewed from our north. Jupiter now orbits the Sun in a nearly circular path at a mean distance of 5.2 AU, where 1 AU is an astronomical unit defined as the distance from the Earth to the Sun. It did not actually form in this position. As realized by celestial mechanics practitioners going back to Isaac Newton, the planets perturb one another, and the elements of their orbits change over time. It used to be supposed that these changes were bounded within reasonable limits. Thus, the great 18th century practitioners of celestial mechanics, such as Joseph-Louis Lagrange and Pierre-Simon Laplace, the latter of nebular hypothesis fame, devoted a great deal of attention to demonstrating the stability of the solar system, in which the planets continued to follow more or less the same orbits forever, rather like a watch that would never run down. It appears, however, that the situation is considerably more complex than previously assumed. Over the past 2 to 3 decades, it has become apparent that the giant planets Jupiter, Saturn, Uranus, and Neptune have migrated within the solar system due to mutual gravitational perturbations. They have exerted force upon one another, resulting in orbital damage to their planetary counterparts. A consequence was the ejection of icy bodies from the inner solar system into the outer regions of the Kuiper Belt and Oort cloud, the cold areas that generate periodic and long-period comets. Their influence extended to the formation of terrestrial planets. Mars originated from the segment of the solar nebula located just inward of Jupiter. Deprived of material akin to an embryo lacking sustenance, proto-Mars remained diminutive. In contrast, the protoplanetary nebula between it and Jupiter, which was expected to generate an additional planet, remained unformed and exists as the unaggregated rocky remnants constituting the asteroid belt. The giant planets contributed material to the inner solar system, resulting in the significant impact event known as heavy bombardment, which occurred approximately 4.1 to 3.8 billion years ago. The Moon, Mercury, and Mars exhibit the remnants of this tumultuous epoch through their extensively cratered landscapes. Despite the Earth's exposure to similar erosive forces from weathering and plate tectonics, only a few recent impact formations remain. Renu Malhotra, currently at the University of Arizona, was the first to challenge the entrenched belief regarding the solar system's stability and the fixed positions of the giant planets. In the 1990s, she focused on elucidating the peculiar orbit of Pluto, which was then regarded as a standard planet. Malhotra, born in New Delhi in 1961, was the progeny of an aircraft engineer employed by Indian Airlines. Following attaining her master's degree in physics from the Indian Institute of Technology, Delhi in 1983, she relocated to the United States to enroll in the PhD program at Cornell University. Her dissertation, finalized in 1988, focused on the moons of Uranus. She secured a postdoctoral position at Caltech under Peter Goldreich, who, along with Scott Tremaine, posited in 1979 that the narrow rings of Uranus were maintained by a set of shepherd satellites. Their theory was initially validated by examining Saturn's narrow F-ring, which is confined between the previously unidentified satellites, Prometheus and Pandora, as revealed by the Voyager flybys. Subsequently, Voyager 2 corroborated this theory during its 1986 flyby of Uranus. In her investigation of Pluto, Malhotra observed that, unlike the orbits of the other principal planets, which are distinctly separated, nearly circular and predominantly coplanar, Pluto's orbit is markedly irregular. Pluto's proximity to the Sun at perihelion varies by nearly 20 AU compared to its distance at aphelion, resulting in approximately 20 years around perihelion, last occurred in 1989, during which it resides within Neptune's orbit. It also undertakes excursions of 8 AU above and 13 AU below the plane of the ecliptic, one of the established conditions. It evaded planetary researchers in the early 20th century. Moreover, due to its substantial satellite, Charon, it is essentially classified as a binary planet. The inquiry pertains to the formation of this binary planet within its unusual orbit in the outer regions of the planetary system. How did it maintain stability once formed? Due to a 3.2 orbital resonance with Neptune, Pluto's outermost giant planet is shielded from detrimental gravitational interactions. The resonance entails Pluto completing precisely 2 orbits for every 3 orbits of Neptune. It was once hypothesized that Pluto could be a former satellite of Neptune, likely expelled during interactions with Neptune's substantial moon Triton, which orbits in a retrograde direction, into its current trajectory. As understanding the Pluto-Charon system's characteristics advanced, the hypothesis of an escaped satellite became increasingly implausible. It appeared probable that Pluto originated in a typical circular orbit with low inclination, alongside numerous similar small icy bodies in the outer solar system. Pluto likely resided far beyond the present 3.2 resonance with Neptune during its formation. Subsequently, chaos ensued. The giant planets, Jupiter, Saturn, Uranus, and Neptune, previously in stable resonant positions, were displaced from those positions by gravitational perturbations caused by the icy material belt in the outer solar system, now referred to as the Kuiper belt, of which Pluto was a part. Saturn, Uranus, and Neptune migrated outward as Jupiter advanced inward. During the epoch of giant planet migration, Pluto and Charon became ensconced in their atypical orbit. Although hinted at by some earlier astronomers, the migration of the giant planets was first clearly and definitively articulated by Malhotra in a 1993 paper on the evolution of Pluto's orbit. Initially, her proposal faced significant skepticism, but it was substantially reinforced by the discovery of exoplanet systems containing hot Jupiters, starting with 51 Pegasi b, just 2 years later. The hot Jupiters were evidently colossal planets that likely originated at a considerable distance from their progenitor stars, before migrating inward to their current locations. There was no longer any justification for skepticism regarding the operation of analogous processes within our solar system. It is understood that the gravitational perturbations of the giant planets initially cleared their formation zones by dispersing the residual mass of planetesimals, the primordial small bodies from which the planets originated. A portion of this mass currently exists in the Oort cloud of comets. However, the majority has been completely lost from the solar system. A planetesimal that scatters outward acquires angular momentum, whereas one that scatters inward relinquishes it to the planets. The planet's scattering of planetesimals results in their orbit's evolution. Most inward scattered objects would have been directed into the gravitational domains of the inner Jovian planets, Uranus, Saturn, and Jupiter. In contrast, some outward scattered objects would have been propelled into the extensive outer spherical cloud of comet nuclei referred to as the Oort cloud, while others would have reverted towards the inner solar system to be reaccredited or rescattered. Jupiter's substantial mass would have rendered it highly effective at ejecting objects from the solar system, particularly eliminating most scattered planetesimals in the Neptune zone. As Neptune interacted with this array of dispersed objects, it would have acquired orbital energy and angular momentum, expanding its orbit. By ejecting these objects throughout the solar system, Jupiter acted as the primary source of Neptune's supplementary angular momentum and energy. However, due to its significantly greater mass, its orbit would have contracted only minimally. In summary, Neptune would have migrated outward, while Jupiter would have moved slightly inward due to these interactions. This situation significantly impacts the dynamic history of the primordial small bodies in the outer solar system, particularly Pluto. As Neptune migrated outward, gravitational perturbations known as resonances would have traversed the outer solar system. Resonance denotes the phenomenon where two orbiting planets possess orbital periods that are small integer ratios of one another, such as 2.1 or 3.2. A comparable instance occurs when an individual on a swing receives a slight push at the same point during each cycle. This push aligns with the swing's natural oscillation frequency, resulting in a significant amplitude increase. If Pluto had originally formed with an orbital radius that allowed the 3-2 resonance to be the first significant Neptune resonance encountered, Pluto, and presumably Charon, which was captured earlier by Pluto, would be ensconced within this resonance with Neptune. Consequently, within its 3.2 resonance zone, Pluto and Charon are effectively insulated from planetary perturbations, remaining securely confined within their protected orbit. It is important to recognize that, as is customary, Jupiter was the principal actor in the dynamics of the early solar system's gravitational interactions due to its immense mass. Jupiter continues to navigate objects throughout the solar system and, in numerous instances, prevents them from impacting Earth. Regardless of its formation location and historical trajectories, Jupiter ranks fifth from the Sun among the planets, situated beyond the 4 terrestrial planets and the failed planet that Jupiter itself inhibited from forming, the asteroid belt. On a moonless night, whether at opposition or not, Jupiter radiates as a faintly yellowish star, equally luminous as any in the sky. It is constant, serene, unwavering, and grand, the unequivocal sovereign of the solar system. Undoubtedly, the illumination emitted by Jupiter merely reflects sunlight. Although it may appear imperial, it is, like all planets, merely a subordinate and attendant to the Sun. Sunlight reaching Jupiter is 27 times less intense than that reaching Earth. How can Jupiter appear so luminous in our sky despite its considerable distance and the faint light it reflects? The mirror analogy implies the solution. There are at least 3 methods to enhance the light reflected by the mirror. In Jupiter, it is unfeasible to position the mirror nearer to the source. The remaining elements enhance the surface's polish and reflectivity or augment the mirror's dimensions. Astronomers quantify the reflectivity of a surface using the term albedo. Albedo is the ratio of light reflected by a surface to the light incident upon that surface. Jupiter's albedo 0.52 is nearly the highest among the planets. In contrast, the albedos of the airless rough surface Mercury and the Moon are 0.11 and 0.12 respectively. For the Earth, it is merely 0.36. Only Venus, enveloped in luminous clouds, exceeds Jupiter's reflectivity of 0.65. While albedo is a contributing factor, the principal reason for Jupiter's apparent luminosity is its size. It is 11 times the Earth's diameter and nearly 1/100th of the Sun's. The Mayans were justified in calling it the Sun of the Night. If it functions as a mirror, it possesses a vast reflective surface. Jupiter's distance from Earth fluctuates as it moves from the near side to the far side of its orbit. Consequently, its apparent diameter varies from approximately 30 arc-seconds during conjunction, when positioned on the opposite side of the Sun, to nearly 51 arc-seconds at its maximum. Consequently, it is invariably larger than Mars. Mars never exhibits an apparent diameter greater than 25 arc-seconds. In contrast, the maximum apparent diameter of Venus surpasses that of Jupiter, attaining 60 arc-seconds, but this occurs during Venus's inferior conjunction between the Earth and the Sun. It subsequently presents its nocturnal hemisphere to us. As a superior planet, Jupiter's disk is never in a crescent or half phase. It is consistently nearly full, with the maximum phase defect occurring at quadrature, when it forms a 90-degree angle with the Earth-Sun line. Jupiter remains 99.1% illuminated, rendering the phase scarcely discernible. A moon that is 99.1% illuminated appears as a full moon to the average observer. These factors render Jupiter one of the most splendid and gratifying subjects for telescopic observation, as it can be favorably observed for a significant portion of the year. This differs from Mars, which radiates brightly at opposition but is a biennial, akin to certain flowering plants. It reaches opposition only once every 2 years and 2 months. Jupiter is a perennial phenomenon, occurring approximately every 399 days. Following a short interval of prominence, Mars diminishes as it distances itself from Earth and approaches conjunction on the opposite side of the Sun, whereas Jupiter retains its brilliance for most of the year. It is indeed the planetary observer's old faithful. It steadfastly retains its powerful dominion. It remains exalted, majestic, and composed, resembling a sun among the other planets. From Jupiter's perspective, Earth would be classified as an inferior planet, perpetually tethered to the Sun. A telescope would reveal its cyclical phases from new to crescent to half to gibbous and back to new. However, solar glare would impede visibility. Its maximum angular separation from the Sun is merely 11 degrees. As observed from Earth, Mercury can attain temperatures of up to 28 degrees. Consequently, our planet, Earth, which holds paramount significance for us, would likely be imperceptible to a hypothetical observer from Jupiter. We are awed by the magnitude of the colossal planet. Understanding an object's perceived size and distance enables the calculation of its diameter. Historically, the observable size of a planet was assessed through a telescope utilizing a micrometer. The distance between spider threads was adjusted by rotating a calibrated screw until the planet's disk precisely fit between them. Conversely, for Jupiter, accompanied by 4 substantial satellites, its diameter can be ascertained by measuring the duration of their transits across its disk. Knowing the apparent diameter allows for the straightforward determination of the actual diameter, provided the planet's distance is known. This is now recognized with a high degree of precision. The distance fluctuates based on Jupiter's orbital position relative to Earth. However, the requisite calculations, while intricate, can be proficiently managed by experts in celestial mechanics. Upon performing the calculations, it becomes evident that Jupiter is exceptionally vast. When depicted to scale on a flat surface, 11 Earths can be arranged side by side with a slight margin remaining. The planets are 3-dimensional, and when incorporating the 3rd dimension, one discovers a more remarkable statistic. The circumference, or the distance around the planet's equatorial diameter, exceeds that from the Earth to the Moon. Upon circumnavigating his planet, a Jovian Magellan would have required 11 times the endurance of a terrestrial counterpart. Educators have historically employed scale models to elucidate the otherwise challenging vastness of the cosmos to their students. In alignment with their educational approach, we present a scale model of the solar system featuring the planets positioned based on their distances from the Sun and proportionately scaled in volume. Consequently, if Mercury is depicted as a pea, Venus and Earth are represented as grapes, whereas Mars is characterized as either a small grape or a large pea. Next is Jupiter, a somewhat oblate cantaloupe. Saturn is smaller, approximately the size of a grapefruit, whereas Uranus and Neptune are similar to a lemon and a lime. From a dynamic perspective, the gravitational influence of one body on the motion of another is determined by the body's mass, such as Jupiter, rather than its mere size. Jupiter's mass is 318 times greater than Earth's, rendering it the most massive planet in the solar system. Its closest competitor, Saturn, is significantly less massive, possessing merely 95 times the mass of Earth. Indeed, if all other celestial bodies, gas giants, terrestrial planets, and various debris such as asteroids and meteoroids, were aggregated on one side of a balance, Jupiter would still outweigh them, causing the scale to tilt in its favor. By all criteria, it is the preeminent planet in the solar system. The solar system can be accurately characterized as a primary approximation, with the Sun and Jupiter as the principal bodies, while the others are merely remnants and debris. In the 1980s, during a significant alignment of the Jovian planets, which facilitated the slingshot maneuver of the Voyager space probes through the outer solar system, much discourse occurred regarding the impact of their collective gravitational influence on Earth. This phenomenon was termed the Jupiter effect, as it involves all planets aligning in one direction, amplifying their influence on individuals. It was unequivocally absurd. Despite Jupiter's substantial mass, its gravitational force diminishes rapidly due to the inverse square law of distance. Despite its relatively low mass, the Moon's differential gravitational attraction induces significantly greater disturbances in the terrestrial realm than Jupiter, particularly evident in ocean tides. The hypothesis that the Jupiter effect could result in global cataclysms was naive. However, it generated greater book sales than those authored by credible experts on planetary science. Although its volume is immense enough to contain 1/300 Earths, Jupiter's composition is relatively dense. Its density is significantly lower than Earth's, which comprises rocky and metallic substances, and has a mean density of 5.5 gccm3. Although Jupiter is thought to possess a comparable rocky core, most of its substantial volume is gaseous. The planet primarily comprises the light elements hydrogen and helium. The average density is approximately 1.33 gccm3, slightly exceeding the density of liquid water, 1 gcm3. This indicates that the massive planet would nearly buoy if situated in an adequately large bathtub capable of accommodating it. Saturn, possessing a merely 0.69 gccm3 density, would indeed float in water, albeit not as effortlessly as a cork, which has a density of only 0.24 gccm3. It was previously believed that the compositions of planets and stars would remain unknown. It transformed following the mid-19th century with the advent of the spectroscope. The spectroscope utilizes a prism or diffraction grating to disperse light from a celestial body into a spectrum of varying wavelengths. Dark lines and bands emerge in a planet's spectrum that can be compared to those in laboratory spectra. Every individual possesses a unique arrangement of fingerprints. Similarly, each element has a distinctive line configuration. This enables the determination of the chemical composition of extraterrestrial bodies through the analysis of their light. V.M. Slipher of the Lowell Observatory significantly advanced in comprehending the composition of Jupiter and other giant planets by documenting dark absorption bands in their spectra during the 1910s and 1920s. The nature of these bands was initially entirely unknown. In the 1930s, German-born astronomer Rupert Wild, who emigrated from Germany after Hitler's rise to power and spent most of his career at Yale University in the United States, identified them as hydrogen-rich compounds, specifically methane and ammonia. Only a few years prior, stellar astronomers had commenced recognizing that stars predominantly consisted of hydrogen and helium. Wild believed that the composition of the gas giants was analogous. Consequently, Jupiter comprises approximately 88% hydrogen and 11% helium. According to Wild, this was the formula for creating a Jupiter. Notably, it is also the approximate formula for the Sun. This is not unexpected, considering Jupiter's formation process involved its rapid growth by accreting a significant quantity of the residual gas from the solar nebula before its dissipation. Their initial mass is the primary distinction between a star like the Sun and a gas giant like Jupiter. Should the mass be sufficiently substantial, the gas will gravitational collapse into a star, thereby successfully commencing thermonuclear reactions in its core. It will evolve into a substellar object, a massive planet, if it lacks sufficient mass. Upon determining a planet's average composition and density, the subsequent step involves analyzing the internal structure by examining the behavior of different materials under pressure. Subsurface materials are typically subjected to significant compression, resulting in a considerably greater density than materials nearer to the surface. Wild additionally addressed this issue during the 1940s and 1950s. His model of Jupiter's internal structure, which remains the foundation for contemporary models with minor modifications, posited a substantial volume of hydrogen and helium gas, encasing a small embedded rocky core. Consequently, Jupiter resembles a baseball composed of tightly wound wool and cotton yarn, encasing a spherical cork core. The observable cloud strata would resemble the sewn cowhide exterior, fulfilling the analogy. Jupiter is the largest gas giant in the solar system and approaches the maximum size permissible for a planet. Increasing Jupiter's mass will result in gravitational compression, leading to a reduction in its diameter. Should the process persist, the pressure within Jupiter's core would rapidly escalate to levels sufficient to initiate thermonuclear reactions, wherein 4 hydrogen atoms are amalgamated into a single helium atom, with the resultant mass differential emitted as energy by the well-known equation E mc2. At this juncture, Jupiter would cease to be classified as a planet and would instead be categorized as a star, thereby rendering the Sun-Jupiter system a prototypical binary star system. Nonetheless, Jupiter may be regarded as a nascent or potential star, as it emits nearly twice the energy it absorbs from the Sun. Although a quantitative assessment of this excess energy output relies on recent measurements with infrared detectors, astronomers such as Richard Anthony Proctor and Percival Lowell speculated that Jupiter and the other gas giants could be nascent stars as early as the 19th century. In the instance of Jupiter, they were largely accurate. Recollect the nascent history of the solar system, during which Jupiter and the other planets commenced their formation from the solar nebula. As matter coalesced to create the initial protoplanetary cores, and as some of these cores expanded and attracted additional matter, evolving from moon-sized to planetary dimensions, the collisions transformed kinetic energy into thermal energy. As Jupiter's swift expansion surpassed its competitors, its core became heated. A significant portion of this heat is anticipated to remain contained. Jupiter functions effectively as an oversized thermos, possessing a limited exposed surface area relative to its mass. Consequently, Jupiter is anticipated to preserve a portion of its primordial heat. Besides the heat generated during its formative stages, Jupiter may continue to produce heat through its current contraction. Compressing a gas generates heat, as evidenced by the warmth of a bicycle pump during operation. To maintain its current energy output, Jupiter must contract by merely 1 millimeter annually, an imperceptible rate for even the most meticulous telescopic observer. A potential heat source could be helium rain, as its condensation and precipitation from Jupiter's atmosphere produce supplementary energy. Jupiter is an unusual planet characterized by the precipitation of liquid helium. Jupiter lacks a solid surface, existing as a gaseous or liquid entity. Only clouds exist within the expansive hydrogen-helium atmosphere, which becomes denser as one descends deeper into the planet. At a depth of several thousand kilometers, temperature and pressure escalate to levels that cause hydrogen to liquefy, a phenomenon that, under standard atmospheric pressures, such as those on Earth, transpires solely at exceedingly low temperatures. Liquid hydrogen, as understood, is classified as a cryogenic substance. On Jupiter, the situation is different. Hot liquid hydrogen is present there. Although the term atmosphere on a gaseous planet is somewhat ambiguous, It will be employed here to denote a relatively thin gaseous layer enveloping an underlying fluid sphere. Since the 17th century, it has been established that Jupiter is large and rotates swiftly. Its rotation, lasting just under 10 hours, is the swiftest of any planet. Consequently, Jupiter's fluidic sphere exhibits an equatorial bulge analogous to a bucket of water that, when swung, allows the liquid to settle at the bottom without spilling a single drop. The force that retains the water at the bottom is called the centrifugal force, meaning the center-fleeing force. Though we call Jupiter a gas giant, it might be more accurate to refer to it as a fluid giant. The technical designation for a sphere compressed at the poles is oblate spheroid. The degree of flattening is typically correlated with the rotational velocity. Consequently, the oblateness is negligible in planets with extremely slow rotation, such as Mercury and Venus. The Earth's value is 1298, while Mars's value is 1170. The relevant figure for Jupiter is 115. Saturn, which rotates nearly as swiftly as Jupiter, exhibits greater flattening. Its oblateness is 1/10. Due to Jupiter's fundamentally fluid composition, various layers exhibit differential rotation. Though not yet substantiated, it is hypothesized that Jupiter's internal structure may be arranged as a series of concentric cylinders, each rotating at varying velocities. This perspective posits that the tops and bottoms of these cylinders become apparent at their intersection with the planet's surface, resulting in the distinct circulation patterns recognized by observers of Jupiter's visible cloud features. Jupiter's diameter measures 143,000 kilometers at the equator and 134,000 kilometers at the poles, revealing the planet's noticeable flattening even through small telescopes. A particle at the equator travels at a velocity of 45,000 kilometers/h, while one at the poles remains stationary. This differential rotation generates alternating circulation patterns, elongating the clouds into strikingly banded formations that captivate telescopic observers. Jupiter's atmosphere is believed to have been acquired from the solar nebula prior to its dissipation, thus reflecting its composition. It predominantly consists of hydrogen, with trace quantities of water vapor, methane, and ammonia. While the majority of the original hydrogen and helium on Earth have dissipated into space, Jupiter has retained them securely. Jupiter's superior retentiveness can be attributed to two factors. First, the temperature at the planet's cloud tops is 130 degrees Celsius, resulting in sluggish molecular and atomic movement. Second, Jupiter's gravitational grip is exceptionally strong, as evidenced by its escape velocity of 60 km/s, in stark contrast to Earth's 11 km/s. No rocket launched from Earth has ever approached the escape velocity required to overcome Jupiter's gravitational influence. It is intriguing to imagine what it would be like to drop into Jupiter. As noted above, there is no solid surface to stand on, and anything that attempted to make a landing would embark on an endless and fatal descent. Of course, no astronaut will ever attempt it, but it can be done, and indeed has been done, by a robotic probe. On 7 December 1995, an atmospheric probe detached from the orbiting Galileo spacecraft and dropped into the clouds in the infernal Jovian depths. The exact point of descent was the south edge of the north equatorial belt. The exact entry spot was 612° north latitude, the location of one of the planet's most ripping or high-speed jet streams. As the probe descended, it remained in contact for just under an hour. Winds were found to increase at deeper levels, confirming that unlike the Earth, where cells of circulation are produced by solar heating, Jupiter's wind system is largely driven by internal heat, as described above. As the probe continued its soundings, it found that, as expected, the pressure continued to increase at lower levels. Finally, at a depth of 155 kilometers below the upper cloud deck, where the pressure increased to some 22 times that of the Earth at sea level, and the temperature rose to 150 degrees C, the doughty little probe succumbed to the extreme conditions. It had given its life to science. At that point, its radio transmitter went silent forever. We can imagine the probe continuing inward descent and ending up, who knows where. Obviously, no matter what the manufacturer's warranty claimed, the metal and fiberglass making up the probe would have been utterly wrecked, reduced to vapor, and mixed around with the rest of the swirling interior of Jupiter before it got much further down than the point where radio contact was lost. Supposing, however, that it was made of sterner stuff and managed to reach all the way to Jupiter's core, it would have found itself among an undifferentiated amalgam of liquid rock, metal, and water, representing the primordial nucleus around which the giant planet formed in the early planet-forming sweepstakes 4.6 billion years ago. Here, at the very center of the planet, the pressure is in the many hundreds of megabars, where 1 bar is the atmospheric pressure at the surface of the Earth, and the temperature is an estimated 30,000 degrees C, which makes it much hotter than the visible surface of the Sun. It would hardly be an inviting place, but then, for that matter, neither would the Earth's center. Based on our previous discussion, it is evident that Jupiter is a complex entity with indistinct boundaries between gas and liquid. We have addressed the majority of what is known about Jupiter's extensive and, in many respects, enigmatic interior, which comprises the majority of the planet's mass. We now shift our focus to the outermost layer of the Jovian structure, which has captivated observers. The slender outer skin encompassing the visible cloud tops. Only the upper 60 kilometers of Jupiter's atmosphere is visible. This region is home to the intricate and captivating array of phenomena that unfold before the observer each night. These phenomena pertain to meteorology and can be comprehended through its overarching themes. A fundamental principle of meteorology asserts that, on a rotating planet like Earth, a gas parcel heated by solar radiation generates a column of ascending air that subsequently expands and cools. As the gas expands, the gas on the equatorial side of the column must traverse a slightly greater distance to encircle the planet than the gas on the polar side. Like horses in distinct racetrack lanes, the one covering the longer distance tends to lag behind. This lane differential induces rotation within the entire gas parcel. Given that the Earth's rotation appears anti-clockwise from a vantage point above the North Pole, the rotation of a rising gas parcel in the northern hemisphere will be clockwise, cyclonic, while in the southern hemisphere it will be anti-clockwise, anti-cyclonic. Visualizing this may require some sketching to fully comprehend the concept, and imagining the horses running in separate lanes may be beneficial. If the planet possesses a typical axial tilt, akin to Earth, gas near the equator experiences greater heating than gas near the poles. Consequently, this phenomenon generates extensive vertical wind motion cells, familiar to mariners. On Earth, easterly trade winds prevail between latitudes 5 degrees and 30 degrees N and S. Temperate westerlies, known as the Roaring Forties, occur between 35 degrees and 50 degrees, and polar easterlies dominate at even higher latitudes. At low latitudes, regions of relative calm, termed the doldrums, 05 degrees N and S, and the horse latitudes, 30-35 degrees N and S, are present. Note, winds are characterized by their originating direction, not their destination. Thus, easterlies flow from east to west, while westerlies flow from west to east. The upper cloud layer is the benchmark for atmospheric pressure on Jupiter, which does not possess a solid surface akin to Earth. The primary energy source is not solar radiation, but rather the internal heat, which, paradoxically from our perspective, originates from below rather than above. While sunlight contributes to minor seasonal fluctuations corresponding to the 12-year Jovian cycle, the effects driven by convection predominate, rendering the impacts of solar insolation less discernible and measurable. In the mid-19th century, Jupiter's internal energy source was strongly suspected, albeit unverified. Despite its distance from the Sun, where solar radiation intensity is merely 4% of that on Earth, numerous observers noted on its surface not the anticipated monotony of a frozen world, but rather the dynamic movement of a turbulent atmosphere, replete with clouds akin to those in Earth's summer sky. As articulated by the Scottish astronomer Charles Piazzi Smith, who observed from the pristine air of Tenerife, Jupiter exhibited the most picturesque clouds. Creating such visually appealing clouds necessitates an energy source in addition to the diminished sunlight. Thus, in 1870, the English popular astronomy author Richard A. Proctor stated, "The vast atmospheric envelope is saturated with vaporous masses influenced by underlying forces. The rapid and frequent disturbances indicate the presence of forces vastly exceeding any that the Sun could exert on such a distant planet. This leads to the conclusion that Jupiter remains a molten body, likely fluid throughout, still bubbling with the intensity of primordial fires, continuously emitting substantial clouds that differ from terrestrial ones. The Jovian clouds are unaffected by solar influence. While Jupiter adheres to the orbital governance of the solar system, it remains autonomous in its internal dynamics. His cloud belts operate as though the Sun were non-existent. They remain unaffected by day and night or the Jovian year. They arrive at will, persist for months, years, or decades, and vanish abruptly. They are sui jovis, generated by vertical currents from the heated core and arranged in longitudinal sequence by Jupiter's rotation. They are self-formed, not solar-formed, condensations of vaporized material from below. Jove is truly the cloud compeller, as his name suggests. Percival demonstrated foresight in this instance. It is challenging to identify any aspect of this assertion that has been corroborated by later studies. As heated gas ascends in columns from below, it dissipates heat through condensation, resulting in cloud eruptions that the differential rotation transforms into vortices, cyclones and anticyclones. These columns are relatively intact in the polar regions, appearing as numerous circular patches. In more temperate latitudes, certain features such as the Great Red Spot and the White Ovals, refer to Chapter 6, maintain their vortex characteristics over extended durations. The majority are smaller and more transient, exhibiting twisting motions, into vibrantly hued festoons, or extending into slender wisps. The elongated characteristics ultimately contribute to the comprehensive bands and zones encircle the planet. The overarching framework is sufficiently comprehensible. However, it is now imperative to transition from generalities to particulars that infuse vitality and nuance into the topic. We will examine the planet's empirical observational history, focusing on Jupiter's extraordinary atmospheric phenomena chronicled by centuries of committed Earth-based observers, predominantly amateurs. The documentation is remarkably abundant. Due to the advantageous conditions that render Jupiter a prominent and appealing subject for observation, no other planet presents such a wealth of information. In the winter of 1610, Galileo Galilei became the inaugural observer of Jupiter through a telescope. He promptly made a remarkable discovery, the planet's 4 largest moons, an observation that profoundly captivated his imagination, as it suggested that Jupiter possessed its own planetary system, distinct from the Sun. Despite the superiority of his telescopes for that era, they could not reveal details of the planet's disk. Another generation elapsed before several Italian astronomers, including Niccolò Zucchi, Evangelista Torricelli, and Francesco Fontana, discerned the planet's distinctive banded pattern. These observations, conducted circa 1630, represented the limitations of the telescopes of that era, the utmost frontier of early 17th century optics. However, they can be readily replicated with any proficient modern telescope, including many infamous department store models. The observational record amassed over nearly 4 centuries since Fontana created his exquisite Giove indicates that the banded backdrop is, while not entirely, at least reasonably stable. Consequently, the illustrations by the Italian-French astronomer Giovanni Cassini and the Dutch astronomer Christian Huygens from the 1660s and 70s are virtually indistinguishable from those produced with small telescopes today. Were the Jovian vistas entirely stable, they would soon cease to be interesting. It is the possibility of change, movement, and novelty that makes any study attractive, and beneath Jupiter's steady-going facade is a restless and dynamic panorama, with the smaller features constantly undergoing change, and even the broader bands and zones subject to dramatic differences in hue, brightness, and appearance. Also, because of the frantic pace of Jupiter's rotation, there is plenty of variety on a single night. Except during the abbreviated nights of midsummer, an observer, with stamina duly fortified at intervals by helpings from a pot of coffee, may peruse the entire globe of Jupiter in the dizzying array between dusk and dawn. Nor does Jupiter look exactly the same night to night, since we are not looking at the solid ground, as on the Moon or Mars, but at the mutable and changing cloud features of an atmosphere. Truly, old Jupiter, staid and majestic as it may seem, is in its cloud deck a world of evanescence and mutability, and every night brings something new and fresh. It is unnecessary to reiterate that in telescopes, regardless of size, our observation of Jupiter is confined to the vibrant cloud layers in its upper atmosphere. The colors that render the planet visually striking also provide insights into the composition of these clouds. We can infer their chemical makeup through visual colorimetry rather than requiring a spectroscope. Trace amounts of compounds known as chromophores generate these colors. Hydrogen and helium, the primary components of Jupiter, are entirely transparent gases. Additionally, helium, being a noble gas, is characterized by its inertness. It does not interact with other atoms to create molecules. Conversely, hydrogen exhibits an opposing temperament. It is highly sociable and gregarious, readily combining with surrounding elements such as oxygen, carbon, nitrogen, or sulfur, constituting less than 1% of the planet's mass. In conjunction with hydrogen, these elements constitute molecules, including water, methane, ammonia, hydrogen sulfide, ammonium hydrosulfide, and numerous organic compounds. It is important to clarify that organic in this context does not signify production by living organisms. It merely refers to compounds containing carbon bonds. These molecules are responsible for the stunning colors observed on Jupiter. In addition to methane, which remains gaseous, a defining feature of these other molecules is their ability to condense under the specific temperature and pressure conditions present in Jupiter's atmosphere. At this condensation level, unable to ascend further, the condensation disperses and creates a cloud layer. Consequently, Jupiter's hues reveal data regarding the existence of trace molecules and the temperature and pressure of the clouds in which they develop. At the altitude of the upper cloud tops, where meteorological and chemical conditions are influenced by solar energy and the significantly diminished heat rising from the interior, temperatures are extremely low, approximately 130 degrees, and the clouds are composed of ammonia ice cirrus. Under equilibrium conditions, ammonia cirrus would appear immaculate white. However, photochemical reactions involving ammonia and methane produce a yellowish-brown smog, contributing to the planet's distinctive yellow and tawny tones. The brownish belts are located at a greater depth, elevated temperature, and increased pressure level. Although it has not been conclusively demonstrated, the ammonia ice above them has likely evaporated, revealing the brownish ammonium hydrosulfide haze beneath. It is widely acknowledged that the pale regions represent high-pressure zones where ammonia ascends and solidifies into creamy ammonia cirrus clouds. Conversely, the belts signify low-pressure areas where downwelling inhibits ammonia from rising, maintaining clarity and revealing the underlying warmer brownish clouds. On Earth, we recognize high and low-pressure systems and can predict incoming weather patterns by observing barometric fluctuations. Conversely, on Jupiter, high and low pressure areas extend into concentric bands due to its swift rotation. Approximately 12 bands, interchanging light regions and dark zones, are always observable. The flow in the belts and zones is markedly turbulent. Rather, it is subjected to significant shearing and vorticity. On a planet where winds howl at half the speed of sound, it is unsurprising that a telescope with a sufficient aperture appears tumultuous chaos. Upon observing this planet, one may envision oneself as articulated by John Milton in Paradise Lost, Book 2. The sport and the quarry. Of tumultuous whirlwinds, eternally submerged beneath the tumultuous sea, bound in chains, destined to engage in perpetual lamentations. In summary, within the upper 60 kilometers of the Jovian cloud layers, there exists a thin weather layer, where solar energy, which influences Earth's weather patterns, is relevant only at the surface, while the remaining circulation is propelled by heat rising from the deeper, warmer fluid regions of the planet's interior. While the background is predominantly stable, comprising bright areas and darker bands, the intricacy of the details is astonishingly complex, with features nested within features akin to Chinese boxes. For over 150 years, backyard observers, particularly members of the British Astronomical Association, and more recently, the American Association of Lunar and Planetary Observers, have diligently maintained meticulous and comprehensive records of the weather on this celestial body from their private observatories and Jovian meteorological stations. The darker belts and brighter zones are designated by a practical, albeit somewhat superficial, nomenclature system, initially adopted by the observers of the British Astronomical Association, BAA, established in 1890, and now too entrenched to be abandoned. The fundamental diagram is presented here. The typically luminous zone, occasionally ochre or tawny, extending 9 degrees on either side of the equator, is referred to as the equatorial zone, EZ, while the darker bands adjacent to it are designated as the north and south equatorial belts, NEB and SEB. The SEB often appears as a double structure, resembling 2 belts rather than one, with the components designated SEB N and SEB S. At elevated latitudes are the north and south tropical zones, NTRZ and STRs, and the north and south temperate belts, NTB and STB, among others. The system starts to deteriorate beyond 45 degrees north and south, where the striped pattern transitions to mottling due to convection cells. Although Italian observations in the early 1630s established the perception of bands, it required an additional generation of telescope advancements before prominent observers such as Robert Hooke, the audacious Christian Huygens, and the ambitious Giovanni Cassini could identify irregularities in the bands and distinct spots that were recognizable across different observing sessions and occasionally from one apparition to another. The irregularities and spots would aid in ascertaining the planet's rotation period. In 1664, Robert Hooke documented a diminutive spot, previously considered the earliest observation of the renowned Great Red Spot, which was named in the 19th century. Nevertheless, Hooke's spot is mislocated. It is situated on the Neb, rather than at the edge of the Seb. A more compelling candidate is a spot observed in 1665 by Giovanni Cassini. At that time, he was in Bologna, Italy, but was soon lured to France in 1669 by Louis XIV or his chief minister Jean-Baptiste Colbert to oversee the Paris Observatory. Cassini's spot is positioned accurately and appears to have been notably enduring. Its longevity has resulted in its designation as the permanent spot. Cassini documented it multiple times between 1665 and the early 1690s, and a feature evidently identical and illustrated as a deep red is present in a 1711 painting by the Italian artist Donato Creti, currently housed in the Vatican Museum. Creti devoted the majority of his career to Bologna, and although Cassini never returned to Italy after 1669, he passed away, entirely blind, in Paris in 1712. He had engaged the artists Jean Patigny and Sébastien Leclerc for the creation of his significant moon map. Creti's painting appears to be grounded in direct telescopic observations. The permanent spot painting was part of a series of small canvases illustrating celestial bodies, commissioned by the Bolognese Count Marsili as gifts for Pope Clement V. These works aimed to inspire the Papal States to establish a public observatory, which ultimately succeeded in constructing the Tower Observatory at the University of Bologna in 1725. Creti's painting dates from 1711. Cassini's nephew, Giacomo Maraldi, conducted an additional observation of the permanent spot at the Paris Observatory in 1713, after which it vanished. Although occasionally associated with the Great Red Spot, its comparatively diminutive size and disappearance post-1713 render this association improbable. It may have been an antecedent feature of a similar nature. During the 17th century, astronomers deliberated the characteristics of the observations made through their telescopes. In his posthumously published work, Cosmotheros, in 1698, Huygens recognized Jupiter as a tempestuous planet, and even contemplated the implications of its meteorological conditions for its Jovian inhabitants. Jupiter has been observed to possess substantial clouds composed of vapors and water, as evidenced by numerous arguments supporting their presence on the planet. Rain occurs there. Otherwise, the vapors evaporated by solar heat would not be detectable. The winds are generated solely by vapors evaporated through heat, and it is evident that they circulate on Jupiter due to the constant motion and diversity of the clouds surrounding it. They must construct tents and huts, or reside in subterranean shelters to safeguard themselves from these threats and ensure peaceful and secure nights. I would not challenge the pride of men by asserting that they are equally skilled architects, possessing equally grand residences and palatial structures as we do. And who are we indeed? Merely a group of insignificant individuals inhabiting a minuscule portion of the world on a planet vastly smaller than Jupiter or Saturn. The clouds exhibited perpetual motion and rapid transformation. Early observers noted dark spots alongside intermittent bright patches, speculating whether they glimpsed the solid surface through the cloud gaps. However, distinguishing the ground from the clouds remained ambiguous. Cassini claimed to have observed Jupiter's snow-covered hills. A century later, the presumptuous William Herschel and Johann Schroeter erroneously assumed that the white regions represented the actual surface, while the dark regions constituted clouds. It was not until the early 19th century that the figure-ground problem, utilizing some psychological terminology, was adequately resolved. The Jovian atmosphere's luminous, fluffy clouds are higher than the darker formations. The initial observers were mistaken and clearly erroneous in their conviction of Jovian inhabitants, a notable farce in history. Although it has frequently been presumed that Cassini's permanent spot from the late 17th century is synonymous with the renowned Great Red Spot, this remains highly uncertain. Giacomo Maraldi observed it in 1713, after which there is no documentation for over a century, a hiatus that, according to John Rogers, director of the Jupiter section of the British Astronomical Association, constitutes an unbridgeable gap. It has been posited that the disappearance of the permanent spot may be linked to the notable absence of sunspots during the same timeframe, known as the Maunder minimum. While interconnected, concealing one enigma within another does not resolve it. For some reason, the records of even meticulous observers like William Herschel, despite his unrestrained arrogance, and Johann Schroeter do not document the Great Red Spot during the time frame of their observations in the late 18th century. Nevertheless, they confirm numerous other captivating Jovian phenomena, and it is difficult to comprehend how they could have overlooked it had it existed. In 1785-6, the meticulous Schroeter documented an occurrence of what he termed schwarzdunkle Flecken, extremely dark small spots. These locations likely represent an early instance of the phenomenon known as blue features, characterized by bluish projections arising from the peripheries of the dark bands. Since 1911, occurrences have consistently been observed on the southern boundary of the North Equatorial Belt, NEB. However, before that, dating back to at least Schroeter's era, they manifested on the opposite side of the equator, specifically on the northern boundary of the South Equatorial Belt, SEB. Nevertheless, Schroeter's comprehensive records provide no evidence of the Great Red Spot. The modern history of the Great Red Spot can be traced back to 1831, when Heinrich Schwabe, a pharmacist in Dessau, now primarily recognized for discovering the 11-year sunspot cycle, documented the distinctive notch or embayment in the sea known as the Red Spot Hollow. Since Schwaber's observation, the holo has consistently indicated the position of the Great Red Spot, even during periods when the spot itself has been obscured. Consequently, the red spot, frequently indistinct, or holo, is depicted in later illustrations by Schwaber. The Reverend William Rutter Dawes, William Huggins, and Lawrence Parsons, the 4th Earl of Ross, created at intervals over the ensuing 4 decades. Until now, the Great Red Spot had not attained any notable recognition, or even been assigned a specific designation. In 1876, the most accurate observations of the planet were transmitted from New Zealand and New South Wales due to its position far south of the celestial equator by the Sydney merchant and yachtsman G.D. Hurst, utilizing a 27-centimeter silvered Newtonian telescope, produced drawings depicting a peculiar luminous reddish feature originating from what is currently designated as the Seb. Hurst's description is significant due to his difficulty perceiving planetary colors. Hurst designated the feature as the fish, based on its shape. His drawing reached the Royal Astronomical Society in 1877, and instrument maker John Browning was so impressed that he framed it and displayed it at the subsequent RAS meeting. Minimal events transpired in 1877, and it was not until the subsequent year that the fish, if indeed it was the same phenomenon, achieved prominence and became, as the Great Red Spot, the preeminent feature on the planet, a name familiar to every schoolboy as noted by Thomas Babington Macaulay. On 9th of July, Carr Waller Pritchett, an ordained Methodist minister, inaugural president of the now-defunct Pritchett College in Glasgow, Missouri, and director of the college's Morrison Observatory, established with a donation from Berenice Morrison, whose maternal grandparents owned a tobacco plantation in Glasgow, was observing the planet with the world-class 30-centimeter Clark refractor when he observed an elliptic, cloud-like mass, distinct from the general outline of the belts. He described the cloud as nearly a perfect oval, predominantly rose-hued. Pritchett's report elicited significant enthusiasm. Initially attracting only a few devotees, Jupiter now enticed hundreds to telescopes to witness what was promoted, in a Carnival Barker manner, as the greatest Jovian feature of all. As it deepened to a vivid brick red, it became known by the name it has intermittently warranted: the Great Red Spot. By 1880, its grand oval contour, which temporarily resembled the ellipsoidal form of a cigar, measured 40,000 kilometers by 13,000 kilometers. To contextualize, 3 Earths could be accommodated side by side with additional space remaining. Edward Emerson Barnard, a young self-taught photographer's assistant in Nashville, Tennessee, was among those captivated by the Great Red Spot, driven by an insatiable desire for astronomical knowledge. Barnard conducted meticulous observations using a 10-centimeter refractor obtained through diligent frugality. The telescope's cost was $380, a substantial sum representing 2/3 of his annual salary at the photography gallery. Barnard resided with his ailing mother in a house with a mansard roof in a bleak and desolate Nashville area, characterized by only one neighbor's proximity. He later reflected on the solitude of the location where he conducted his observations, which frequently instilled a sense of dread as he was out at all-night hours. Barnard observed Jupiter during the years 1879 and 1880. In August 1879, he discovered the Great Red Spot in molten iron. Simultaneously, it was experiencing alterations in its oval shape, the ends intermittently manifested as rounded or pointed, tapering into slender trails. The Great Red Spot was observed to repel nearby features that approached it. Following its peak length in 1880 and its most intense hue a year after that, the Great Red Spot declined in 1882, remaining perilously close to obscurity for the subsequent years. The exceptional performance may have concluded. A revival occurred in 1891. Since then, the Great Red Spot has been conspicuous during specific intervals, namely from 1961 to 1975, 1989 to 1990, and again from 2013 to 2014, while at other times, such as in 1977, 1991, and 2011 to 2012, it has been nearly imperceptible. Nevertheless, the notch-like red spot hollow in the Seb has consistently indicated its location. During 1879-80, the Great Red Spot extended nearly 35 degrees of Jovian longitude. Since then, it has been diminishing. By the period of the Voyager 1 and 2 flybys in 1979-80, its length had diminished to 21 degrees. By then, it had deteriorated so that only one Earth could fit instead of 3. By 2013-14, it had diminished to a mere 13.6 degrees, resulting in a length of only 15,900 kilometers. The Great Red Spot serves as a quintessential illustration of other vortex phenomena on Jupiter, differentiated solely by its magnitude and duration. It rotates like a terrestrial storm, revolving like a ball bearing between opposing wind currents to its north and south. The spin direction is counterclockwise, as anticipated for a high-pressure storm in the southern hemisphere of a prograde rotating planet. As smaller vortices approach the Great Red Spot, some are diverted, while others orbit it multiple times before ultimately being engulfed. Their inward spirals are captivating to observe and instrumental in ascertaining the sequential timings of their rotation periods around the Great Red Spot. The rotation period of the Great Red Spot has fluctuated over time. During the Voyager missions, 1979-80, the duration was 6 to 8 days, correlating with an average wind speed at the perimeter of 120 magnetomes, 270 mm. By 2013-14, as the spot continued to diminish, it had reduced to 3.6 days, with an average wind velocity of 144 mph. The maximum mean wind velocity in the Great Red Spot is 165 mph, recorded by the Galileo orbiter in 2000. The variations in the rotation period of the Great Red Spot are thought to result from the vortex acquiring rotational energy by consuming smaller spots carried by the northern jet stream of the neighboring South Temperate Belt, STB. The mid-latitudes of Jupiter exhibit analogous storm-like characteristics. However, none can rival the Great Red Spot. The lyrics of the classic Cole Porter song, "You're the Top," it may have included a reference. Among Jovian features, the most emblematic are the Colosseum and the Louvre Museum. Nonetheless, despite its prolonged existence, well into its second century since achieving peak development around 1880, it is significantly diminished from its former state. When WS first observed it in 1965, it was readily visible through a 60mm refractor at a magnification of merely 35x. However, in recent years, it has become increasingly difficult to discern, even with 15 to 20 cm reflectors. Observers should relish the experience, as its duration remains uncertain. Like veteran soldiers, Great Red Spots persist indefinitely. They merely diminish over time. The Great Red Spot, which emerged in 1878, elicited various intriguing theories due to its need for more understanding. Camille Flammarion, the French astronomy popularizer with a private observatory in Juvisy, observed Jupiter from one of its remote moons. The white circle on the right limb represents Ganymede, accompanied by its shadow. The grey disk to the left of the center denotes Kalisto, which appears notably dark due to its low albedo when contrasted with the planet's luminous surface. The Great Red Spot is located near the center. In 1909, Percival Lowell, known for his controversial theories, articulated his perspectives on the characteristics of the Great Red Spot while describing photographs of Jupiter taken at his Flagstaff Observatory. Observing the extraordinary persistence of the spot, formerly known as the Great Red Spot Hollow, he remarked, "The hollow is clearly identifiable in the illustrations by Sir William Huggins created in 1859-1860, which he graciously provided to me. This presents evidence of a characteristic that, in its overall structure, has remained stable and enduring for 50 years, an impressive duration for a cloud formation to persist. This alone would illustrate that Jupiter's meteorological conditions are independent of the Sun." The Sun's cradle subsequently transformed into the nucleus of a substantial reddish mass, which eventually vanished, restoring it to its original state. This phenomenon suggested a violent eruption from beneath, after which the cloud veil, torn during the explosion, descended once more, obscuring the furnace from view. The permanence of the feature suggests a degree of plasticity, contrasting with what we call gaseous in composition, and resembles the enduring sites of disturbance with which we are acquainted on Earth. The behavior suggests that it is a nascent volcano. It establishes a connection between volcanoes and sunspots. In his other writings, Lowell reiterated Flammarion's concept of a continent in formation, describing the Great Red Spot as a sort of juvenile elephantine volcano or geyser, manifesting its youth in fluid rather than solid conditions, yet relatively stable, a fragment of kindergarten geology. Although such notions may appear simplistic today, they were not entirely erroneous. The Great Red Spot is a type of volcano, specifically of a Jovian nature. It rises prominently above an eruption or the ascent of hot material from beneath. Following the emergence of the Great Red Spot, Jupiter, previously the domain of a few enthusiasts, finally garnered the recognition its size and significant position in the solar system warranted. For nearly a century, amateurs have played a pivotal role in these studies and continue to make significant contributions to this day. The astronomical literature extensively documents the remarkable contributions of amateurs. However, fame is ephemeral, and many who significantly enhanced our comprehension of the giant planet still need to be recognized. Nathaniel Green, Arthur Stanley Williams, William Frederick Denning, Theodore E. R. Phillips, Bertrand M. Peake, and F. J. Hargreaves are merely appellations. We owe them a significant debt, as their documentation of the planet's cloud characteristics has been essential to our comprehension of its long-term meteorology and continues to inform us today. Initially, examining Jupiter with even a basic instrument appears formidable. The vast amount of details and the dramatic nature of the extensive changes appear beyond the capacity of the human eye-brain-hand system to adequately comprehend. Furthermore, the prospective student of the planet, who revisits the historical accounts of the Jupiter section of the BAA, seeking inspiration and guidance on technique, encounters a daunting reality. Despite the planet's visual splendor and intricate details surpassing all objects except the Moon, historical records have predominantly featured meticulous tables documenting the timings of spots along central meridians, calculated rotation periods, and charts illustrating longitudinal drifts. Perusing these memoirs evokes the sensation of encountering a chronicle rather than a narrative. It is exceedingly tempting to avert one's gaze in revulsion, reminiscent of the teachings of a monotonous instructor. Each subject acquires the hue of its admirers. The cartography of the Moon has attracted numerous enthusiasts, eager to document every minute detail, often overlooking the broader context. Jupiter has also established its distinct type, defined by Arthur Stanley Williams, a British solicitor and a prominent figure in Jupiter research. A Brighton native, he began observing Jupiter in his adolescence, and like many of his contemporaries, was captivated by the Great Red Spot's striking emergence. Nonetheless, his rigorous study began solely in 1886-1887. He was significantly inspired by the establishment of the BAA in 1890, and quickly emerged as a prominent member. Despite possessing instrumentation that was modest by any measure, most of his observations were conducted with a 16.5 cm reflector, which, although equatorially mounted, lacked a clock drive. It was accurate regarding Williams, as C.P. Snow remarked that Ernest Rutherford utilized remarkably simple apparatus, yet maximized its potential to the fullest extent. In the final year of his life, Williams ultimately obtained a superior instrument, a 23 cm reflector. Despite having a discerning eye, Williams was an exceptionally clumsy draftsman. Unlike Nathaniel Green, a prominent Jupiter observer and professional portrait artist known for his artistic color drawings of Jupiter, Williams created purely pragmatic drawings. Bertrand M. Peake aptly described them in a 1938 BAA memoir as diagrammatic rather than pictorial. In this instance, necessity demonstrated its role as the catalyst for innovation. Rather than meticulously documenting the precise configuration of the various features, Williams visually estimated, to the nearest minute, the time at which each feature crossed Jupiter's central meridian to examine the presence of wind currents on the planet. The memoirs of the Jupiter section of the BAA adopted a narrative quality. He calculated the rotation periods of specific features by tracking a feature across multiple transits and graphing its observed transit times. He identified the independent drift at various planet latitudes, utilizing each feature as a windsock to investigate the Jovian winds. Williams endeavored to remain as theoretical as possible. He warned that when he employed the term surface material, he intended to imply no judgment regarding its characteristics by the term. This refers solely to the material at Jupiter's visible surface, without addressing whether this material is at the planet's solid or liquid surface, assuming such a solid or liquid surface can be defined. His prudence was commendable. Regrettably, he incorporated the terms canal and channel into the Jovian nomenclature, terms that would subsequently generate considerable controversy regarding Mars. Fortunately, these terms did not gain traction, and the characteristics he labelled canals were subsequently more accurately termed wisps by the British amateur Scriven Bolton. Conversely, the term barge is occasionally employed, accurately depicting the Jovian feature it references, while also evoking Williams's favoured dwelling, a houseboat, in his later years. The substantial effort required for timing and data reduction was, in the era preceding calculators and computers, immensely significant, as Williams noted, though its true significance can only be fully understood by those who have conducted and analysed, for instance, 1,000 determinations of the longitudes of various markings. By 1896, Williams had advanced to identifying 9 distinct currents on Jupiter, as detailed in his seminal paper on the drift of material in different latitudes of Jupiter. Monitoring Jupiter would have afforded Williams little time for other pursuits besides his legal duties. A solitary and resolute man is depicted, persevering in pursuing his unique inclination. Like numerous distinguished amateur observers such as W.F. Denning and Percy Molesworth, Williams remained unmarried. He was in truth a multifaceted individual with various equally captivating pursuits. He cherished the ocean. Upon his retirement, Williams resided in St. Mawes, Cornwall, aboard a barge named the Queen, with his observatory situated nearby on the shore. In 1920, he was awarded the Challenge Cup, the premier accolade in global cruising, for a solo voyage covering 2,000 kilometers from Falmouth to Vigo and back. Upon his demise in 1938, his remains, by his explicit wishes, were transported by steamer to a location off Falmouth, a few miles from shore, and consigned to the ocean in the presence of only 2 companions. Williams's paper on Jupiter's circulation motivated various members of the BAA to pursue similar research. One individual was Denning, as previously mentioned. As a professional accountant, he would have been adept at maintaining the detailed records necessary to monitor the weather on a planet like Jupiter. Like Williams, possessing a retiring disposition, he relinquished a promising cricket career to engage in astronomy. Subsequently, he resided independently in Bristol with his valet and achieved considerable success despite financial constraints and poor health. A note by British astronomical historian Richard Baum aids in resurrecting the memory of the late W.H. Stevenson, a prominent English amateur, who visited Denning to find a solitary older man seated by his fireside. James Muirden, author of the Amateur Astronomer's Handbook, recounted that narrative, noted that Muirden's father resided a few streets from Denning, and distinctly recalled how the street urchins would jeer and insult him on his journey home. Major Percy Molesworth, a prominent individual of the late 19th and early 20th century, was born in Ceylon, now Sri Lanka, and educated in England in preparation for a military career. He was stationed in England and Hong Kong before being reassigned to Ceylon. As an army engineer stationed in Trincomalee, he utilized a large reflector in his garden in that near-equatorial region. Despite occasionally being absent for months due to active service, he appeared to enjoy considerable leisure time and, lacking the responsibilities of a wife or family, was an unrelenting observer of the moon and planets. Jupiter undoubtedly received considerable attention. In 1900, Molesworth recorded 6,758 timings of features traversing the central meridian, and subsequently spent months meticulously calculating the rotation periods of these features based on the timings. Upon his retirement in 1906, he had achieved the rank of Major. Regrettably, he persisted in imposing excessive demands on himself. He continued to exert himself excessively, and in the oppressive climate, this compromised his health. He succumbed to dysentery in 1908 at the age of merely 41. A feature documented by Molesworth on Jupiter has attained legendary status. This phenomenon was designated as the South Tropical Disturbance and is considered one of the most renowned features ever documented on Earth, following the Great Red Spot. Molesworth observed that 1900 the South Tropical Zone was among the most luminous zones, distinct and brilliant, brightening to a milky white where it adjoins the South Equatorial Belt. However, by February 1901, its appearance had altered. A series of dark humps emerged along the southern edge of the South Equatorial Belt, and by May, one of these humps had evolved into a dark shading extending across the South Tropical Zone to the South Tropical Belt. This dark region of the belt was notably unique and became referred to as the South Tropical Disturbance. The South Tropical Disturbance, having a marginally shorter duration than the Great Red Spot, periodically approached it. Rather than overlapping, it appeared to leap across and reconstituted entirely on the opposite side. The South Tropical Disturbance was notable for obstructing the trajectory of smaller entities, which upon nearing were redirected to their original path. The South Tropical Disturbance was enduring and persisted until 1940. Subsequently, analogous disturbances have occurred, notably between 1955 and 1958 and between 1978 and 1983. The latter coincidentally coincided with the Voyager flybys, allowing for comprehensive analysis. A South Tropical Disturbance now links the retrograding South Equatorial Belt South Jet Stream to the prograding South Tropical Belt North Jet Stream, resulting in the circulating current. In 1901, the inaugural year of the new century, a remarkable new talent emerged in Jovian studies. The Reverend Theodore Evelyn Rees Phillips assumed the role of director of the BAA Jupiter section, a position he held until 1934. Phillips was a tall, slender, somewhat austere figure, a type not uncommon among the Anglican clergy of that era. Appearances were misleading. In truth, he was unassuming and modest, and as noted by another adept artist astronomer E, he was also remarkably Jupiter-like. Monsieur Antoniadi, on 21 May 1901, utilized the 24 cm refractor at Camille Flammarion's observatory in Juvisy, near Paris. This illustrates the red spot situated within its depression. The concentration of dark matter to the right constitutes a segment of the South Tropical Disturbance, which emerged during this period. In 1914, he commenced the amalgamation of transit observations, the timing of features across Jupiter's central meridian, conducted by the most proficient observers to construct more dependable drift charts. 2 years later, he assumed the role of vicar at Headley, near Epsom, Surrey, where he established a private observatory outfitted with a 20 cm refractor and the same 50 cm reflector previously utilized by the renowned astronomer-artist Nathaniel Green. Following Phillips, notable Jupiter observers have encompassed Bertrand M. Peake, an exceptional mathematics scholar and tennis player at Cambridge, who served with the Hampshire Regiment during the First World War and subsequently became a headmaster at Solihull, near Birmingham, and F.J. Hargreaves, a patent agent in Coulsdon, transitioned to a professional telescope manufacturer. They epitomized British culture. One envisions the trio, Phillips clad in a black suit and rigid white clerical collar, the others adorned in tweed, enjoying afternoon tea on the lawn. For 4 decades, they maintained exceptional records of the planet's meteorology, a feat rendered even more extraordinary by the infamous fluctuations of British weather. In the memoirs of the BAA in 1940, Peake encapsulated the contributions of this team and other BAA observers. There appears to be no other published series of planetary observations that can be compared, as they provide, from 1901 onwards, at the latest, an uninterrupted record of the appearance and motion of surface features throughout the entire period that Jupiter was observable. Any scholar of Jovian meteorology must consult these memoirs for the essential data to support their research, as it is unavailable elsewhere. The period during which Phillips, Hargreaves, and Peake were active represented the zenith of the Bar's Jupiter section. The planet was formerly known as the Amateur's Planet, but it is no longer so. Nonetheless, their valiant endeavour did not endure beyond the Second World War. The nerve centre of Jupiter studies, Phillips's Headley, located in the home counties, incurred significant damage. Phillips's church was subjected to bombardment, and a V-1 buzz bomb struck the rectory. Being present must have been anxiety-inducing, yet it did not occur. Possibly accelerated by the occurrences of that dreadful period, Phillips's health commenced to deteriorate. He passed away in 1942. Peake, who succeeded him as director of the BAA Jupiter section in 1934, dismantled his observatory in 1947 due to declining health. He retained the directorship of the BAA Jupiter section and continued to generate memoirs for the section for an additional 2 years. He subsequently commenced writing a book titled The Planet Jupiter. Published in 1958, it served as the authoritative account of the planet until the advent of the spacecraft era, and it still holds value today. T.H. cited it in his doctoral dissertation. The BAA section maintained a limited number of active members following Peake's retirement and Jupiter's trajectory, which shifted it to a more southerly position in the British sky. Between 1949 and 1963, Elmer J. Rees, an American, conducted the most superior observations of Jupiter. Following his service in the United States Army Ordnance during World War II, he returned to his hometown of Uniontown, Pennsylvania, where he worked in his family's grocery store during the day and engaged in astronomical observation at night, using a 15-centimeter homemade reflector. This instrument was smaller by 1 seminitos than the one utilized by Williams. When wielded effectively, such an instrument's potential to facilitate significant research underscores Jupiter's extensive exploration opportunities. Rees gained recognition for the precision of his illustrations and transit timings. From 1947, he served as the inaugural Jupiter section recorder of the newly established Association of Lunar and Planetary Observers, ALPO, a role in which he was accountable for compiling most of the section's reports. Interestingly, the leaders of the BAA observing sections are referred to as directors, whereas those of the ALPO observing sections are termed recorders. Rees made numerous observations of the south temperate white ovals, which emerged in the early 1940s. He also examined the significant SEB disturbances and resurgences, returns of the belt from obscurity to prominence. In 1963, despite lacking formal qualifications, he was invited to participate in the Planetary Research Group at New Mexico State University, directed by Clyde Tombaugh and Bradford Smith. He contributed to one of the inaugural professional initiatives to observe Jupiter, consistently capturing images of the planet with a 61-centimeter reflector and establishing the foundation for the Voyager spacecraft missions. At the time of his death in 2010, at 91, he had the gratification of witnessing the successful conclusion of the 2 Pioneer missions to Jupiter, along with the Voyager and Galileo orbiter missions. Subsequently, multiple probes have approached Jupiter en route to other destinations, Cassini towards Saturn and New Horizons towards Pluto, while another orbiter, Juno, commenced its orbit around Jupiter on 4 July 2016. Although Arthur Stanley Williams is renowned for identifying the 9 primary currents of Jupiter's wind circulation, comprehensive understanding has predominantly been the endeavor of his successors, with teams analyzing data obtained from spacecraft. A minimum of 19 currents have now been identified between latitudes 60 degrees north and south, many of which were initially documented by the Voyager space probes. The wind currents appear to be exceptionally stable over time. No discrepancies were observed between the measurements the Voyager and Hubble space telescopes took during the same Jovian season, despite a 12-year interval, equivalent to one Jovian year. In summary, the fundamental framework of Jovian meteorology indicates that the luminous zones, characterized by ascending atmospheric currents, correspond to high-pressure regions, whereas the darker belts, associated with descending currents, represent low-pressure areas. A meteorologist specializing in Earth sciences may experience confusion. On the surface, high pressure correlates with descending air, while low pressure is linked to ascending air. It is essential to recognize that on Jupiter, conditions differ significantly. There is no solid surface, and pressure is measured at the cloud tops. The belts and zones are generally associated with the slow currents identified by Williams and recognized by other visual observers of the planet. According to BAA Jupiter Section Director John H. Rogers, the currents exhibit greater invariance than the belts, characterized by moderate wind speeds determined by the movements of large ovals and other features. These slow currents correspond with a single belt-zone pair. The sluggish currents coexist with a pattern of significantly swifter east-west currents, known as jets or jet streams, which constitute the essential framework of the belt-zone pattern. The jet streams occasionally exhibit outbreaks of small spots, revealing their positions to visual observers. The intricate details were disclosed solely when the Voyagers captured images of the fine cloud texture, which exhibited a continuous zigzag pattern of winds alternating between eastward and westward jet streams. The former pertains to the enduring boundaries of the belts and zones. Although the small-scale features exhibit a flow pattern, larger formations, specifically vortices that roll between the jet streams, disrupt it. Although numerous rotation periods for different cloud features were collected by planet observers until the 1950s, the reference frame, the Jovian counterpart of the Greenwich Prime Meridian, had to be established arbitrarily due to the absence of a discernible solid surface. For convenience, the planet has long been divided into two primary latitude zones. The longitudes of locations approximately 9 degrees north or south of the equator, influenced by the Great Equatorial Current, were computed using System Y, with a period of 9 hours, 50 minutes, and 30.0 seconds. The longitudes of locations at elevated latitudes were computed using System 2, totaling 9 hours, 55 minutes, and 40.6 seconds. The mean rotation period of the Great Red Spot in 1890-91, when the scheme was first implemented, is referenced here. This classification of the planet into systems 1 and 2 provides a fairly accurate understanding of the average relative drift of features within the two regions, although individual spots within each zone exhibit independent motions. In 1955, radio astronomers conclusively determined the rotation of the planet's core. Intense, intermittent bursts of radio frequency energy were recorded deep within the planet's interior. This study established an additional system of longitude, System 3, characterized by 9 hours, 55 minutes, and 29.4 seconds, linked to the planet's core, rather than its observable cloud formations. The revelation of the planet's core's rotation period represented a significant advancement. Comprehensive modeling of the planet's circulation became feasible for the first time. John H. Rogers categorizes the currents observed visually into 3 distinct types. The primary equatorial current traverses the equatorial zone between approximately 10 degrees north and 10 degrees south, advancing eastward at 7 to 8 degrees per day, around 100 MNRS, relative to System 2, with occasional intermediate speeds noted along its periphery. Secondly, the 9 sluggish currents regulate most observable characteristics beyond the equatorial zone, exhibiting velocities not exceeding 5 degrees per day, 10 meters. Third, jet streams exist at the peripheries of specific belts, observable solely during rare minor dark spots, exhibiting velocities of several degrees per day, 170 mantis. These are now recognized as permanent. According to Voyager's findings, corroborated by Galileo, the planet's maximum wind velocities occur in 2 narrow jet streams in the equatorial zone, EZ, at 6 degrees to 7 degrees north and south of the equator, attaining speeds of 170 mph. In the northern hemisphere, as one moves away from the equator, the winds diminish and reverse direction. At approximately 15 degrees north, they shift to a westward flow, ranging from 25 to 70 nms. At approximately 20 degrees north latitude, an additional narrow eastward jet with wind speeds exceeding 150 mph, alongside other eastward jets at 36 degrees and 38 degrees north, exists. In increasingly higher latitudes, extending to the pole, the winds diminish consistently. In the southern hemisphere, the positions and velocities of the jets differ somewhat from those in the northern hemisphere. The westward jet is situated at 17.5 degrees south. Jovian meteorology. As previously mentioned, the Great Red Spot's remarkable persistence led to the belief that it was connected to an underlying surface feature, potentially an erupting volcano, as proposed by Percival Lowell. Nevertheless, this concept is incompatible with the spot's longitudinal drift, which experiences intermittent markings and decelerations. Consequently, it progressed more swiftly between 1920 and 1940 than in contemporary years, and as initially observed by the British amateur Jupiter expert Bertrand Pique, the red spot darkens in hue when its velocity decreases. Recognizing that these wanderings demonstrate it cannot be affixed to the surface, Pique hypothesized that the spot might be a solid entity buoyant like an egg in saline water. It was an appealing concept, yet it ultimately proved entirely erroneous. The Great Red Spot is, in essence, a distinctive atmospheric phenomenon. The Great Red Spot is a prominent high-pressure region with cloud tops that rise several kilometers higher and are cooler than the surrounding Jovian clouds. The Great Spot may transport significant heat from the planet's interior to its upper atmosphere, analogous to how a hurricane extracts heat from a warm ocean. As anticipated by American amateur Elmer J. Rees through observations with a 15 cm reflector in 1949, and subsequently confirmed in the 1970s by Rees, Bradford Smith, and Gordon Solberg through photographic studies at New Mexico State University, the Great Red Spot exhibits internal rotation akin to that of a hurricane. The Great Red Spot rotates in an anticyclonic direction in the southern hemisphere. When Rees and Smith published their findings, the rotation period was 6 days, with wind speeds of approximately 100 mph. The Great Red Spot vortex is confined within a narrow latitude range of 15.4 degrees to 25.4 degrees south by two opposing jets that are significantly deflected to either side, resulting in the sharply defined oval shape of the Great Red Spot. Smaller eddies approaching the Great Red Spot from the east are typically redirected around its northern perimeter. However, as they progress toward the western edge of the spot, some are entrained into the circumferential current, depositing white ice that creates a collar of white clouds. The spot's darker interior is characterized by small convection cells, occasionally observable by visual observers or captured by CCD imagers utilizing large instruments. Aside from its longevity, the most intriguing mystery of the Great Red Spot is its coloration. A long-standing theory posits that the coloration may result from chemicals generated deep within the planet and brought to the upper cloud layers. Molecules comprising sulfur or phosphorus alongside organic compounds were prominent candidates, while lightning was proposed as an energy source for molecular transformation. A recent analysis by Kevin Baines and his colleagues at the Jet Propulsion Laboratory of data from the Cassini probe, which passed by Jupiter en route to Saturn in December 2000, indicates that the reddish material in the Great Red Spot may be restricted to the upper layers of the clouds. Furthermore, the reddish substance closely resembles a compound synthesized in the laboratory through ultraviolet irradiation of ammonia and acetylene gases, both prevalent in the nebulous upper atmosphere of the giant planet. The reddish substance is not a towering column of cloud or a volcanic eruption, but rather a superficial glaze. Deeper layers likely consist of whitish or grayish clouds. In the Great Red Spot, ammonia ice is elevated to greater altitudes in the atmosphere, where it is less protected from the sun's ultraviolet radiation. Moreover, the intense winds linked to the vortex motion entrap reddish compounds, hindering their escape and intensifying the coloration. The variable intensity of the red spot's coloration seems to result from fluctuations in the volume of the white cloud it is absorbing. Indeed, since its peak in the 1870s and 80s, when it exhibited a sausage or cigar-like shape, the Great Red Spot has experienced significant transformations. It has increasingly become less elongated over time, although this process has been somewhat uniform. From 1996 to 2015, it exhibited a reduced tendency to contract in a north-south direction and adopted a more rounded shape. Consequently, it resembled a rugby ball more than an American football. John Rogers reports that the internal circulation period of the spot has diminished, as evidenced by his observations of grey streaks and other characteristics. Consequently, the 6-day period identified by Rees and Smith in the early 1970s has diminished to 4.5 days in 2006 and further to 4.0 days in 2012. Nevertheless, the angular momentum of the spot remains unchanged. Thus, analogous to a skater retracting her arms, the peripheral wind velocities within the spot have escalated. In recent years, they have recorded speeds ranging from 270 to 430 to 680 km/h. In contrast, terrestrial hurricanes, such as the catastrophic Hurricane Katrina of 2005, which made landfall in New Orleans with wind speeds of 185 km/h, would appear almost as a mild zephyr by Jovian standards. Jupiter is, as Huygens described, a tempestuous planet. Despite the Great Red Spot's reduction to 50% of its original size, its interaction with various features and spots, alterations in its drift rate, and a recent decrease in its internal rotation period, it has paradoxically sustained a consistent longitudinal oscillation of 90 days throughout the monitoring period. The Great Red Spot is undoubtedly the most enduring atmospheric phenomenon on Jupiter. Its long-term dynamical stability is partially attributed to its proximity to the equator and the lack of ground friction. Nevertheless, several other locations have also demonstrated considerable longevity. The most exemplary instances among these are the white ovals. The white ovals are anticyclonic systems closely linked to the South Temperate Belt, STB, which delineates the region's southern boundary traversed by the Great Red Spot. Their history originates in 1939 when, according to BAA Jupiter section records, the STB was unusually bright. However, it exhibited 3 brownish segments, designated as AB, CD, and EF. By the late 1940s, it became apparent that as the segments dispersed, the lighter intervals between them evolved into structured cloud systems. The white ovals, FA, BC, and DE. They drift eastward relative to the Great Red Spot, overtaking and passing south of it approximately every 2.6 years. Furthermore, as each moved within a slightly distinct period, they approached or receded from one another without converging. Consequently, BC neared within 50 degrine of the longitude of FA in 1975, receding as FA commenced acceleration. For several years, the white ovals seemed to be diminishing, and it was widely anticipated that they would disintegrate due to atmospheric turbulence upon descending below a specific critical size threshold. Subsequently, following a sequence of interactions from 1998 to 2000, BC, DE, and FA unexpectedly merged into a singular large white oval. This is a detailed examination of the red spot, Junior, created when 3 enduring white ovals coalesced and altered in hue. On 11 December 2016, the Juno spacecraft captured this remarkable image during its 3rd flyby of Jupiter, revealing a perspective 16,600 kilometers above the planet's cloud tops. In February 2006, the white oval BA experienced a color transformation to red, initially observed by planetary imager Christopher Go, an amateur astronomer from Cebu, Philippines. This event elicited significant interest from both amateur and professional astronomers. The color alteration was likely attributable to the heightened elevation of the post-merger feature and intensified winds. Since then, the feature known as red spot, Junior, has predominantly been observed as red, although it has occasionally appeared predominantly white with only a hint of reddish hue. Both amateur and professional observations indicate that the movement of this anticyclonic feature is significantly influenced by segments of the South Temperate Belt, STB, colliding with it. These developments are indicative, and it is evident in this sequence of events, a plausible scenario for forming the Great Red Spot. Alongside the renowned white ovals, numerous smaller eddies exist, most appearing and dissipating swiftly, representing the transient characteristics of a Jovian summer's day. Some exhibit greater longevity and can be tracked from one Jovian apparition to the subsequent one. The enduring characteristics comprise a distinct series of white ovals in the South-South Temperate Zone, SEZ, and a persistent white oval in the North Tropical Zone referred to as White Spot Z, WSS, which amalgamated with another oval in 2013, resulting in the merged feature becoming pale red. A sequence indicative of a potential incarnation of the Great Red Spot occurred when another white oval in the South Equatorial Belt, SEB, experienced a color transformation to red in May 2009. However, mere months later, it collided with the Great Red Spot, which seemingly deemed it unpalatable and expelled it. Consequently, the expelled spot reverted to its original white oval coloration. The existence of a Jovian anticyclone is characterized by ruthless competition for survival, embodying a harsh and unforgiving reality. The equatorial zone, EZ, delineates the area of the vigorous equatorial current, part of System I, which propels features at a velocity of 8 degrees of longitude per day about features in other regions of the planet. The equatorial zone is delineated to the south by the South Equatorial Belt, SEB, and the north by the North Equatorial Belt, NEB. Throughout the majority of the 20th century, and into the 21st, the Neb has been the most notable belt on the planet, characterized by various dark projections, plumes, festoons, or blue features, along its northern boundary. Nonetheless, the polarity was inverted in the late 18th and 19th centuries. The sea was more pronounced, exhibiting blue plumes along its southern edge. The reversal occurred in 1911. The SEB experiences a significant cycle of diminishing and restoration to its previous intensity. A review of historical records reveals multiple cycles that transpired in the 19th century, particularly 1869, 1873, and 1882. No evidence of cycles exists between 1882 and 1918, during which the sea constituted the planet's widest and typically darkest belt. A significant transformation occurred in late 1918. The southern portion of the sea abruptly disappeared from sight, rendering the entire area intensely white. In December 1919, a series of dark humps appeared, centered at longitude 230 degrees on the northern component of the SEB. On 27th of February 1920, Harold Thompson, then director of the BAA Mars section and a dedicated observer of Jupiter, stated, "The SEB is a most extraordinary spectacle. The composition predominantly features circular dark dots and white spots. The dark and white spots exhibited retrograde motion, and the rapid changes in appearance rendered it nearly impossible to discern the markings after a brief interval of merely a couple of days. The entire area previously occupied by the faded SEB was now in disarray, transforming into a labyrinth of dark spots and white ovals. Dark material continued to emanate from the source at 230-degree longitude and dispersed due to wind shear from east to west at a rate of several degrees per day. In the subsequent weeks, this wave of darkness entirely enveloped the planet. The SEB regained its original prominence following the conclusion of this seemingly eruptive process. Subsequent violent outbreaks were noted in 1928 and 1943, initiating a new cycle characterized by regular occurrences at 3-year intervals until 1958. Subsequent outbreaks occurred in 1971 and 1975. The latter, which WS observed with keen interest using a 20-centimeter reflector, was notably vigorous and involved an unprecedented 4 sources. A separate SEB disturbance in 1978 was independently identified by WS, succeeded by a pause in the 1980s. Subsequent outbreaks transpired in 1991 and 1993. At the time of this writing, the latest event transpired after 2010. Elmer J. Rees proposed in 1949 that the disturbances in the south equatorial belt, which consistently commence with the abrupt emergence of a small dark spot near the central latitude of the belt, may originate from material ascending to the surface due to an eruption. At that time, the rotation period of the planet's core, 9 hours, 55 minutes, and 29.4 seconds, establishing a third system of longitudes, System 3, had not yet been identified. Radio astronomers initially discerned this from Jovian radio bursts in 1955. Rees did not reanalyze his data until 1972. Initially, he attempted to chart the source longitudes within System 2, necessitating the identification of a distinct pattern. He subsequently replotted them in System 3. This time, he discovered that the sources corresponded to 3 distinct loci, A, B, and C, gradually drifting relative to the core and exhibiting a consistent rotation period of 9 hours, 55 minutes, and 30.1 seconds. The 1975 revival aligned with Rees's eruption hypothesis. The outbreak sources were located within 2 degrees of the longitude of loci A and B, while a third source, locus C, was situated 23 degrees east of locus B. Rogers posited that the agreement was optimal if locus B had shifted 20 degrees in post-1958. The origins of the 1990 and 1993 eruptions also closely aligned with locus B. Locus A appears to be the origin of the most significant revivals, 1919, 1928, 1971, and 1975, while locus C is the least robust. In revivals with multiple eruptions, such as in 1975, the sequential spot outbreaks occur in the following order. First from locus A, then from locus B, and finally from locus C. We have yet to ascertain the nature of the sources. Initially, Rees proposed they could be volcanoes, referencing Percival Lowell's concept of the Great Red Spot as a volcano in embryo, and Richard Proctor's description of a planet bubbling and seething with the intensity of primeval fires. However, Bar Jupiter section director John Rogers cautions that they cannot be classified as volcanoes in the conventional sense. Rather, they could potentially be enduring sea waves or even submerged objects at significant depths. He further states that regardless of the nature of Rees's sources, the instability invariably manifests first above them, akin to how clouds on Earth initially coalesce over mountains. The SEB disturbances and the intricate cloud formations offer terrestrial observers a unique insight into the tumultuous processes occurring within Jupiter's interior. Alongside the SEB revivals, Jupiter's most remarkable transient phenomena have encompassed instances of significant fading succeeded by revivals of the North Temperate Belt, NTB, and the North Equatorial Belt, NEB. The NTB revivals are signaled by the emergence of a rapidly advancing plume on the NTB jet along the southern boundary of that belt. Conversely, the NEB revivals occur after prolonged disturbances. NTB revivals occurred in 2007 and 2012, while SEB revivals have transpired in recent years. As of November 2016, Jupiter has recently transitioned from superior conjunction with the Sun. The recent NTB revival is currently in progress, characterized by a series of luminous spots on the belt, now observable through telescopic monitoring in the morning sky. It will be intriguing to observe whether, as anticipated, NEB and SEB disturbances ensue. Historically, disturbances in the SEB, NTB, and NEB have been considered unrelated. However, research by Agustín Sánchez La Vega, a planetary astronomer at the Higher Technical School of Engineering in Bilbao, Spain, and his colleagues indicates that they share a similar convective origin. This conclusion appears unequivocal. A persistent enigma is the reason behind the frequent occurrence of SEB and NTB cycles within a year of one another, as well as their correlation with pronounced coloration in the equatorial region, which has led Rogers to describe this phenomenon as global upheaval. Notably, the global upheaval characteristic is illustrated in WS's series of drawings depicting the events of 1975. Ongoing research is being conducted. We now possess sufficient knowledge of Jovian conditions to interpret the meticulous documentation of phenomena recorded by dedicated observers of the planet. We have previously delineated the stratification of clouds within the upper approximately 60 kilometer that we can examine directly, commencing from the frigid ammonia ice cloud deck at the apex and descending through the probable dense ammonium hydrosulfide layer of the brownish bands. Cloud formations proliferate and swirl in the wind in regions between eastward and westward flowing currents. The eddies exhibit significant instability under turbulent Jovian conditions, typically persisting for merely 1 or 2 days before being disintegrated by the intense zonal jets. Nevertheless, despite the volatility of the cloud formations, the zonal jets exhibit remarkable stability, having retained nearly constant positions and wind velocities since Stanley Williams first charted them in 1896. The most profound characteristics observable in the Jovian atmosphere, potentially 100 km beneath the ammonia cirrus of the upper cloud layer, are dark projections, plumes or blue features. At any given moment, 12 to 14 of these plumes are spaced at intervals of 25 degrees to 35 degrees in longitude. In the infrared spectrum, they manifest as hotspots, demonstrating that they are cloud-free holes penetrating the upper ammonia cirrus and ammonium hydrosulfide cloud layers. They reach depths of approximately 100 kilometers beneath Jupiter's troposphere, with heat from below through them. Previous scholars of the planet, including the late José Olivares of Alpo, whose enthusiasm for these characteristics prompted his peers to colloquially designate them as the Olivares blue features, hypothesized that the bluish hue resulted from these areas being occupied by ascending crystals of water ice, essentially commonplace snow originating from deeper layers. On 7th of December 1995, an opportunity to evaluate these theories arose when the Galileo atmospheric probe commenced its significant descent into the Jovian atmosphere, entering through a plume at the southern edge of the nebula. The latitude of 6.5 degrees north delineated the boundary between the ES and the Neb, signifying the position of one of Earth's most intense jet streams. The probe encountered intensified winds at lower altitudes, proving that Jupiter's wind system is predominantly fueled by internal heat, unlike Earth, where circulation cells are generated by solar heating. The probe maintained communication with the orbiting mothership for less than 1 hour. Upon contact loss, it descended 155 kilometers beneath the upper cloud layer, where the atmospheric pressure was 22 times that of Earth's sea level, 22 bars. Its signal was severed, and it vanished beneath the tumultuous clouds indefinitely. During its turbulent descent, the probe discovered minimal evidence of the 3 hypothesized cloud layers: ammonia, ammonium hydrosulfide, and water. This was not wholly unexpected, as the probe had entered a clearing. Nonetheless, the most notable and unforeseen discovery was the extreme aridity of the Jovian atmosphere. It was previously believed that the planet possessed a substantial water reserve, potentially 10 times greater than the Sun's. However, it now seems to have less than the solar abundance. Could communication with the probe have ceased before it arrived at the water? While that may be accurate, it significantly impacts models of planetary origins. As previously believed, Jupiter must have formed rapidly from the solar nebula rather than gradually accumulating by aggregating numerous small water-bearing bodies like comets. If recent calculations indicate that a Jupiter core the size of the Moon formed within 100,000 years of the solar system's inception and attained nearly its current mass of 318 Earth masses in likely less than 10 million years, then from the outset, the planet was positioned to assume a central role as the solar system's narrative developed. We can characterize planetary systems surrounding other stars and observe significant variability among them. Our solar system, featuring a massive planet in a nearly circular orbit just beyond the water ice condensation threshold, approximately 5 AU, is remarkably atypical, contrary to expectations. Astronomers initially sought systems comparable to our own, which resulted in their oversight of more prevalent configurations. Some exoplanetary systems featured widely spaced planets, while others contained multiple Uranus-sized planets nearby. A prevalent scenario involved giant planets in highly elliptical orbits near their stars. The phenomenon of hot Jupiters was not even foreseen by theorists. Numerous systems exhibit intrinsic instability. 2 early exoplanet systems identified are stable: the Solar System, comprising 4 giant planets, and the Upsilon Andromeda system, which contains 3. The celestial bodies of our solar system have been orbiting securely for 4.6 billion years, whereas Upsilon Andromeda and its planets are estimated to be 2 to 3 billion years old, yet they appear to have narrowly escaped long-term instability. Computer simulations conducted by Rory Barnes and Thomas Quinn at the University of Washington in 2001 indicate that approximately 15 to 20% of planetary systems that initially resemble these two will experience disruption within just 1 million years. They propose that generally planetary systems exist on the brink of instability. This may indicate that planetary systems are densely populated with planets, suggesting that the planet formation process is so efficient that an overabundance of planets is produced, necessitating the ejection of some before the others can stabilize into a marginally stable configuration. The giant planets in our solar system have undergone migration, as previously indicated. One consequence of this migration was the expulsion of a 5th gas giant from the solar system. It is traversing interstellar space, a solitary planet detached from our comprehension. As previously mentioned from the outset, Jupiter established. Its authoritative presence was palpable. In the absence of that presence, computer simulations of planetary formation indicate that several massive planets would have traversed the inner solar system, hot Jupiters, or at the very least, hot giants, comparable to Uranus and Neptune, akin to those observed in numerous other systems. Upon the inclusion of Jupiter in the calculations, 2 terrestrial planets resembling Earth and Venus are likely to form, in addition to 1 small planet in proximity to the Sun, Mercury, and another within Mars' orbit. However, planet formation beyond Mars' orbit is significantly disrupted. Rather than a new planet, a fragmented collection of rocky remnants emerged, the asteroid belt. The entire planetary system, including Earth, reflects the influence of its most dominant member, Jupiter. Earth's history, and potentially its future, is closely linked to that of Jupiter. The pressure at the apex of the yellow and tawny zones of the Jovian clouds is approximately equivalent to that of Earth's atmosphere at sea level. At increased depths, both pressure and temperature consistently escalate. The planet's internal structure is primarily dictated by the behavior of hydrogen under progressively extreme conditions. Jupiter is composed of 90% hydrogen by volume, making it the most prevalent element in the universe, followed by helium in a distant second place. The ratio of hydrogen to helium in Jupiter is 9.1, similar to solar and cosmic abundances. The atmosphere is somewhat deficient in helium. Hydrogen exists as a gas solely in the planet's outermost layer, extending to a depth of approximately 1,000 kilometers. At increased depths, it becomes liquid. Ultimately, at approximately 15,000 kilometers, the pressure attains 2 million times that of Earth's atmosphere, 2,000,000 bars, at which stage hydrogen is converted into a viscous metallic state. It is intended to serve as a conductor of electrons. Only limited amounts of this substance have been synthesized in the laboratory, and only momentarily due to the extreme conditions required for its production. The rotation of the 56,000-kilometer thick metallic hydrogen mantle generates potent electric currents and creates a formidable magnetic field. The magnetic poles of Jupiter are. The rotational poles are tilted by 10 degrees. The cause remains unidentified. The faint radio noise detected by radio astronomers was associated with the core rotation. This core rotation delineates System 3. A rocky and metallic core, estimated to be 5 to 10 Earth masses, is believed to reside at the planet's center, encased by a 3,000-kilometer layer of heated ices. This rocky and metallic nucleus serves as the foundation for Jupiter's formation. The temperature is 30,000 degrees C, and the pressure is approximately 100 million times that of Earth's sea level atmosphere, around 100 megabars. The pressure in this environment is so immense that the core would be compressed into a volume smaller than Earth's, resulting in diamond, the least compressible material, being subjected to a density exceeding that of lead at Earth's ambient temperatures. Despite Jupiter's magnetic field being 20,000 times more potent than Earth's due to its significantly larger size, the magnetic lines of flux are considerably more dispersed, resulting in a magnetic force at the uppermost layer of its visible atmosphere, Jupiter's closest equivalent to a surface, that is merely 15 times stronger than that of Earth. Furthermore, a compass needle in Jupiter's northern hemisphere would orient southward due to Jupiter's magnetic field possessing an opposite polarity to Earth. Magnetic polarity is not a static characteristic. The Earth's last reversal occurred approximately 780,000 years ago, whereas Jupiter's may have reversed as recently as 1911, when the polarity of plume features shifted from the northern edge of the Seb to the southern edge of the Neb, as previously detailed. Jupiter's formidable magnetic field significantly influences its surrounding environment and generates phenomena akin to Earth's Van Allen radiation belts. However, Jupiter's radiation belts are vastly more pronounced. The radiation intensity within these belts is so extreme that an unfortunate astronaut traversing them would not survive, facing an exposure of 1,000 times the lethal dose for humans. A gas composed of charged particles is termed plasma. The plasma constituting the solar wind is captured and ensnared in spirals along magnetic field lines. As the lightest charged particles, electrons are accelerated, emitting intense bursts of electromagnetic radiation, synchrotron radiation, in the radio spectrum, first identified by astronomers in the mid-1950s. Certain electrons are accelerated to velocities nearing the speed of light. Due to Jupiter's magnetic axis being inclined approximately 10 degrees relative to its rotational axis, the radio signal exhibits a wobble. The variation period of this signal was determined to correspond to the core's rotation. The interaction of the solar wind with Jupiter's magnetic field forms a vast cavity known as the Magnetosphere. Other planets, including Earth, possess magnetospheres. However, Jupiter's is significantly larger than those of any other planet, and is the largest in the solar system, excluding that of the Sun. The heliosphere is the spatial region influenced by the solar wind and the Sun's magnetic field. Its outermost boundary, termed the heliopause, marks the point where the solar wind interacts with the interstellar medium, which comprises plasmas and magnetic fields from the Milky Way. Jupiter's magnetosphere extends approximately 7 million kilometers toward the Sun, and nearly reaches Saturn's orbit in the opposite direction, representing the largest continuous structure in the solar system besides the heliosphere. In other terms, Jupiter's magnetosphere extends to a radius 100 times that of the planet itself. Its volume is so vast that if our eyes could detect radio emissions, it would appear to cover twice the apparent diameter of the Sun in our sky. It is sufficiently expansive to encompass the orbits of the planet's moons, with charged particles from their surfaces being drawn into the magnetosphere. Jupiter's moon Io, characterized by active volcanoes that release substantial quantities of sulfur dioxide gas into the surrounding space, creates a large, flattened torus of charged particles around Jupiter. This torus amplifies Jupiter's radio bursts through electrical discharges, akin to lightning strikes between Io and the planet. Consequently, the signal's intensity is heightened whenever Io occupies specific positions in its orbit. Charged particles confined within Jupiter's magnetic field, regardless of origin, oscillate between the planet's magnetic poles and generate spectacular aurorae analogous to Earth's northern and southern lights upon interacting with the upper atmosphere. Notably, Jupiter's aurorae exhibit significantly greater intensity. They have been detected across the entire electromagnetic spectrum, encompassing infrared, visible, ultraviolet, and even X-ray wavelengths. In the ultraviolet spectrum, they are 1,000 times more luminous than Earth's. The rings of Jupiter. Saturn is primarily recognized for its magnificent ring system. Initially, it was presumed to be singular, making Earth's observation of such beauty a rare privilege. However, as scientific progress has revealed, ring systems are relatively ubiquitous. In our solar system, all the gas giants, Jupiter, Uranus, and Neptune, also possess rings. Saturn's rings were first identified by telescopic observers in the 17th century. The subsequent discovery was of Uranus's rings in 1977, followed by Jupiter's rings, unveiled by the Voyager missions in 1979–80. In 1960, Russian astronomer S.K. Vseksviatsky hypothesized that a faint dark line at Jupiter's equator, known as the equatorial band, might represent the shadow of an unseen Jovian ring. While this conjecture was plausible then, it is now understood that the equatorial band is a meteorological phenomenon, and the ring shadow is too faint to be detected from Earth. Jupiter's rings exemplify tenuity. They are remarkably insubstantial, especially compared to those of Saturn and Uranus, and were only revealed as the Voyager spacecraft passed by the planet and observed against the Sun. From this unprecedented perspective, dust and ice particles became visible through forward-scattered light, akin to how dirt and smudges on a car windshield are illuminated when driving into the sunrise or sunset. More recently, New Horizons, en route to Pluto, successfully captured images of the rings for the first time from the sunward side. The Jovian ring system comprises 4 elements. A primary ring situated between 123,000 and 128,940 kilometers from the planet, a duo of exceedingly faint outer rings known as the gossamer rings, a toroidal inner ring referred to as the halo. Each structure is fragile and dusty, so insubstantial that it is partially transparent. The observation that they forward scatter more light than they reflect indicates that the constituent particles are minuscule, akin to those found in terrestrial fog. The minuscule particles constituting the rings are believed to be dust ejected by collisions on Jupiter's minor satellites, whose orbits delineate each ring's outer boundary. Except for the halo, each ring is associated with one or more satellites. The gossamer rings are confined by the orbits of Amalthea and Thebe. Adrastea and Metis border the outer limits of the main ring. The minute particles comprising the rings cannot maintain stability for extended periods. The solar wind and the uppermost layers of Jupiter's outer atmosphere undoubtedly exert drag on them, causing them to spiral inward toward the planet, where they are ultimately lost, incinerating in a fleeting display as meteors in the upper atmosphere and contributing marginally to the giant planet's mass. Through such mechanisms, the rings would entirely dissipate within a few million years, if not replenished by excavating new material from satellite impacts. What is the age of the rings? Like ourselves, where every particle is said to renew every 7 years, the rings can be considered both youthful and ancient. They are extremely youthful because the particles are relatively recent additions resulting from impacts. Yet they are also extremely ancient, as the small satellites that orbit closely around Jupiter, such as Amalthea, Thebe, Adrastea, and Metis, are thought to have originated from a circumplanetary disk that existed during the early solar system. Consequently, the Jovian rings, sustained in equilibrium through processes of loss and regeneration, are likely to have persisted since the inception of the solar system 4.6 billion years ago. Satellites of Jupiter. The 4 largest satellites of Jupiter, each exceeding the size of Earth's moon, were identified by Galileo Galilei in January 1610 and designated the Medicean stars in honor of his patron, Cosimo de' Medici. For an extended period, Galileo's assertion of the discovery was contested by Simon Mayer, also referred to as Marius, a German observer from Ansbach. Marius has independently discovered them, and since he documented the dates of his observations in the Julian calendar instead of the Gregorian calendar utilized by Galileo, his notes' dates are 10 days before those of Galileo. At that time, dates in the Julian calendar were 10 days earlier than those in the Gregorian calendar. Upon conversion of Marius's dates, it was revealed that his notes commenced 1 day after Galileo's. A crucial aspect is that Galileo was significantly ahead in disseminating his observations. His Sidereus Nuncius was published in early 1610, while Marius's Mundus Iovalis was not released until 1614. Consequently, as lamented by Galileo's competitor, the Austrian Jesuit Christoph Scheiner, Marius's assertion emerged in vain and too late. Marius merits greater recognition in this history, as he designated the 4 satellites after Jupiter's consorts, despite their designation as the Galilean satellites. Their names and their sequence of proximity to the planet can be recalled through the subsequent verse by Marius himself. Io, Europa, Ganymede, and Kalisto also indulged Jove's desires. Marius abstained from endorsing the Copernican theory, which posits that the Earth orbits the Sun due to the stars appearing as disks in his small telescope. The disks are now recognized as illusory and result from an optical phenomenon. If the stars exhibited disks, they would have to be unreasonably large if Copernicus's heliocentric model were accurate. Marius and many contemporaries endorsed the Tychonic theory, positing that the planets orbited the Sun while the Sun revolved around the Earth. Like Marius and other telescopic observers, Galileo observed the diminutive stellar disks. Nevertheless, he did not interpret them literally. He concluded that they were likely the result of an optical aberration, although he did not fully understand the exact rationale. As the most prominent advocate of the Copernican theory of his era, he perceived the Jovian satellites as a diminutive representation of the solar system and articulated this in Sidereus Nuncius. We possess a compelling and remarkable rationale for alleviating the reservations of those who accept with composure. The revolution of the planets around the Sun in the Copernican system is significantly disrupted by one moon orbiting the Earth. In this scenario, a singular planet orbits another, while our perspective reveals 4 celestial bodies traversing around Jupiter, akin to the moon's orbit around Earth. Jupiter orbits the Sun in a substantial circular path over 12 years. In the diminutive telescopes of the early 17th century, the Galilean satellites appeared akin to stars. Galileo designates them as stars and collectively refers to them as the Medicean stars. The term satellite was introduced by Johannes Kepler in a pamphlet titled Narratio de observation quatuor Jovis satellites erroneus, published several months after Sidereus Nuncius, wherein Kepler detailed his own observational endeavors. Even with his notoriously deficient vision, he achieved success. Contemporary opera glasses or binoculars can reveal them, and it is purported that the 2 most distant, Ganymede and Kalisto, may be discerned with the unaided eye under exceptional conditions. The authors promptly clarify that they have never engaged in such actions. Even a 15-centimeter reflector reveals the 4 Galilean moons as diminutive disks, and it remains perpetually intriguing to observe the transits of the satellites and their shadows across the planet, the eclipses that transpire when the satellites enter Jupiter's shadow, and the occultations that occur when they move behind the colossal planet. Occasionally, one satellite may obscure another. In small telescopes, satellite shadows appear uniformly black. However, each satellite exhibits a distinct appearance during transit. Io and Europa are comparatively bright and often blend into the luminous clouds. Nonetheless, they are readily discernible in projection against darker cloud formations, whereas Ganymede and Kalisto are sufficiently dim that they may occasionally be confused with shadows. Old observers frequently remarked upon dark transits, nearly as obscure as shadows, believing an underlying mystery existed. The perceived darkness of the satellites during their passage across the disk is merely a result of contrast with the more luminous background clouds against which they are viewed. Historically, satellite phenomena have held significant importance. During the 18th century, tables detailing the positions of the Galilean satellites, computed about a standard meridian, such as Greenwich or Paris, were juxtaposed with telescopic observations made by navigators and explorers at remote locations across the Earth's oceans as part of a broader initiative to ascertain the observer's longitude. In 1676, during the measurement of satellite eclipses to enhance astronomical tables, Ole Rømer, a Danish astronomer at the Paris Observatory, identified a discrepancy between the anticipated and actual timings. He elucidated this discrepancy by postulating that light traverses at a finite velocity rather than traveling instantaneously, as previously believed. Consequently, traversing the distance from Jupiter required a finite duration, which would increase with the planet's distance from Earth. It is now established that light travels at 299,792,458 ms, which defines the meter, or 9.460730 x 10 to 1112 ms year, which defines the light year. Light and all forms of electromagnetic radiation, including radio waves, cannot exceed a certain speed. Consequently, even at its closest approach, Jupiter's light takes at least 32 minutes to reach Earth. When Jupiter is positioned on the opposite side of the Sun, it requires nearly 17 additional minutes, totaling 49, to reach us. Should an unseen object collide with Jupiter and produce a flash, we will not be informed of the occurrence until at least 32 minutes post-event. The Galilean satellites are substantial for their category, and would resemble terrestrial planets if not captured in Jupiter's orbits. Consequently, Ganymede, the largest of the four, has a diameter of 5,268 kilometers, surpassing Mercury's diameter of 4,180 kilometers, whereas Kalisto, at 4,020 kilometers, is slightly smaller. They seem diminutive solely about the colossal planet they encircle. Kalisto, the farthest of the Galilean moons, is located 1,183,000 kilometers from Jupiter and has an orbital period of 16.7 days. The density is approximately 1.8 Grazing. Ganymede has a similar density, whereas Europa and Io exhibit densities of 3.0 and 3.5 GCM3 respectively, which are twice as high. These satellites are evidently not gas giants, possessing densities comparable to water's, yet they are also not terrestrial bodies. The Earth's density is 5.5 GCM3. Based on their intermediate densities and locations, it can be inferred that they constitute a distinct category of solar system bodies, composed of rock, metal, and ice, rather than solely rock and metal like the terrestrial planets, or gas like the giant planets. Within this compositional spectrum, Ganymede and Kalisto possess a significant ice content. Kalisto is estimated to be 50% ice, whereas Europa and Io exhibit a more rocky composition. Ice typically exhibits a shiny appearance, whereas Kalisto does not. Ice, primarily frozen water, is contaminated and unsuitable for carbonated beverages or wine coolers. Like the other Galilean moons, Kalisto has developed a mantle of water ice, or liquid water at elevated temperatures and insulated depths, encasing a rocky metallic core. Its surface is dark and punctuated by craters, exhibiting the highest crater density in the solar system. It is, in fact, saturated with craters, indicating that a new crater can only form by destroying or overlapping an existing one. This can only be true if Kalisto's surface is ancient. A palimpsest documenting a succession of explosive events resulting from impacts with smaller celestial bodies dispersed throughout the solar system since its inception 4.6 billion years ago, exhibiting minimal potential for turnover or resurfacing due to internal geological processes. Kalisto exhibits the marks of innumerable epochs of trauma. It seemingly lacks the expertise of a qualified therapist. At first glance, Kalisto appears akin to our Moon, exhibiting significant cratering from meteoroids and comets traversing the solar system. However, a more detailed examination reveals that the craters resemble the indentations left by a hammer striking ice rather than those created by explosive rock fragmentation. Certain features are extensive and evidently document significant shocks. Numerous multi-ring basins exist, such as Mare Orientale on the Moon. The principal one, Valhalla, is encircled by fragmented ridges extending 1,500 kilometers from the center. Nevertheless, the relief remains muted even in the contours of such characteristics. The crust consists of water ice, which possesses inferior tensile strength compared to rock. Notwithstanding the surface's deteriorated state and considerable age, there is significantly less dramatic relief than Mercury and the Moon, and the terminator appears exceptionally smooth. Despite its worn appearance, many of the oldest features have certainly been erased by erosion. Every Galilean possesses distinct characteristics. We shift from Kalisto's cratered icy surface to Ganymede, the largest moon in the solar system, with a sense of relief. Ganymede orbits Jupiter at a distance of 1,070,000 kilometers, with an orbital period of 7.15 days. Ganymede possesses an icy surface, yet its structure is significantly more intricate. It features primitive areas that are dark, heavily cratered, and named after the discoverers of Jovian satellites. Consequently, a Galileo Regio, a Marius Regio, a Perrine Regio, and a Nicholson Regio exist. The ancient, darker crust has fragmented into polygonal plates, delineated by areas of luminous, grooved terrain known as sulci. The grooves are aligned parallel to the polygonal edges of the ancient terrain. What transpired here? Numerous possibilities exist. A straightforward analogy suggests that, as anyone who has filled an ice cube tray to capacity understands, ice expands upon freezing. Did Ganymede, at any point in its history, undergo expansion? If that is the case, the grooved terrain would have occupied the areas where the previous crust could not envelop the satellite. The grooves are comparable to stretch marks. Another possibility is that the varied terrains mimic the solid lava-filled basins and highland regions of the Moon, with ice serving as the equivalent of lava on Ganymede. Although both theories may be erroneous, Ganymede's geological activity has ceased despite enduring alterations. In comparison to the comparatively mundane landscape of Kalisto, characterized by uniformity, implies a narrative akin to Ganymede's. The geological features become increasingly intriguing as we delve deeper into the Galilean satellites. Europa, located 671,000 kilometers from Jupiter and possessing an orbital period of 3.55 days, is the most aesthetically pleasing of the Jovian moons. It is a bespoke and meticulously designed blown glass paperweight. Kalisto and Ganymede exhibit low albedo, whereas Europa possesses a comparatively high albedo of 0.64, nearly matching that of the exceptionally luminous, cloud-covered planet Venus. This indicates that, unlike its outer siblings, Europa's surface is relatively young, possibly between 20 million and 180 million years old. Consequently, Europa exhibits a scarcity of craters. The minimal relief indicates a comparatively recent pristine crust. This crust is interlaced with fissures akin to the thin ice that blankets the Earth's Arctic Ocean sections. Multiple explanations exist for this situation. It is possible that Europa has not completely frozen to its core. A liquid mantle may still be present just beneath Europa's visible surface. The 2013 discovery of 200-kilometer-high geysers in Hubble Space Telescope images near Europa's southern pole increased the likelihood that Europa possesses a global saline ocean, making it potentially the only other celestial body in the solar system, aside from Earth, with such a feature. However, other Galilean moons may harbor similar crust-covered oceans beneath varying ice thicknesses. Consequently, Europa has emerged as the most promising celestial body beyond Earth for the search for extraterrestrial life, garnering substantial funding from both NASA and the European Space Agency, which are presently exploring the feasibility of conducting a series of flyby missions to conduct a comprehensive analysis of its surface in the 2020s. NASA's mission has been designated the Europa Clipper. One can envision a future space probe that penetrates Europa's ice layer, assuming it is thin, and subsequently navigates the ocean in search of its potential inhabitants. We have only recently acquired knowledge regarding the characteristics of the Earth's ocean at its greatest depths. What is concealed beneath Europa's surface? Subsequent to Europa, anything would be an anticlimactic experience. Nonetheless, Io is even more enthralling. It is arguably the most peculiar satellite in the entire solar system. Io, the innermost Galilean moon, orbits Jupiter at a distance of 422,000 kilometers and has an orbital period of merely 1.8 days. Consequently, on alternating nights, it traverses between the two hemispheres of the planet. The other Galileans are nearly devoid of color. Io is not. It is significantly more vibrant than the other Galileans. This is evident even in a modest telescope. It appears distinctly yellowish. The effect is undeniable upon close inspection, appearing almost garish. At close range, it resembles a pepperoni pizza that has seen better days. Io exhibits an absence of impact craters. Its surface experiences perpetual renewal. Therefore, it remains as pristine as this morning's news, with insufficient time for impact craters to form. There are circular formations resembling sinkholes, and herein lies a narrative. In March 1979, during the Voyager 1 flyby of Jupiter, Linda Morabito, then serving as the cognizant engineer for the Optical Navigation Image Processing System, ONIPS, on the Voyager navigation team, was analyzing the initial photographs of Io transmitted to Earth, not to investigate its physical attributes, but to ascertain its edge for navigational objectives. Consequently, she examined images where the satellite was off-center, yet the satellite's limb was distinctly visible. Unexpectedly, she could not fit a smooth curve to the satellite's limb due to an umbrella-shaped plume extending 270 kilometers above the surface. It resembled an erupting volcano. And indeed it was an erupting volcano. The discovery was entirely unforeseen and fortuitous. Nonetheless, Morabito, an associate professor at Victor Valley College in Victorville, California, was not simply fortunate during the writing process. Io is perpetually erupting and currently remains in a state of eruption. All volcanic sinkholes are calderas. Although it astonished many astronomers, active volcanoes on Io were not wholly unforeseen. In a paper released 3 days before the Voyager 1 flyby, Stanton Peele, Patrick Casson, and Ray Reynolds proposed that Io's interior could be molten due to tidal interactions with Europa and Ganymede. In their own expressions, calculations indicate that Io may be the solar system's most intensely heated terrestrial body. Pervasive and repeated volcanism could transpire, resulting in significant differentiation and outgassing. Peele and his associates were expanding upon the understanding that, as established since the era of William Herschel, all Galilean satellites exhibit synchronous rotation concerning Jupiter and orbit in nearly circular paths, aligned closely with the planet's equatorial plane. The three inner moons, Io, Europa, and Ganymede, exhibit a 4.21 orbital resonance. Conversely, Kalisto is the anomalous satellite. Consequently, each time Io traverses the orbits of Europa or Ganymede, it experiences a gravitational pull from them that slightly displaces its trajectory. However, Jupiter, steadfast in its authority over its subordinate, reasserts its dominance like a dog on a leash. This planetary tug-of-war induces friction within Io's interior. The generated heat is adequate to liquefy the rock. The lighter, more volatile elements were expelled to the surface long ago and have evaporated. Consequently, the outermost layers of its crust are abundant in sulfur compounds, which contribute to the vivid warm hues that adorn the satellite's surface. Yellow sulfur is expected to appear almost white at the low temperatures characteristic of Io's distance from the Sun. Yellow sulfur transitions to an orange-red hue upon heating and exhibits increased viscosity. At elevated temperatures, it transforms into a black liquid. All of these hues are present on Io. 8 active volcanoes were identified during the Voyager 1 flyby. The largest Linda Morabito discovered is Pele, named after the Hawaiian goddess of fire. They were designated as Prometheus, Loki, Volund, Amirani, Maui, and Marduk. Masubi. 4 months after Voyager 2's arrival, Pele had entered a state of quiescence, while the other volcanoes continued to erupt. Notably, Prometheus and Loki exhibited increased activity. numerous new volcanoes have been identified as Earth observations persist. Loki exhibits significant activity and features a black lake of liquid sulfur approximately 250 kilometers in diameter, within which solid sulfur icebergs are suspended. Loki, formerly designated as Loki Patera, is the solar system's most potent, continuously active volcano. These features are termed volcanoes. However, they function more akin to geysers, redistributing surface material from Io over considerable distances due to its low gravity, approximately 1/6 that of Earth, or comparable to the Moon's surface. Gas and dust from Io's volcanoes are estimated to be ejected at velocities ranging from 0.5 to 1 km/s, significantly surpassing those of the most powerful terrestrial volcanoes, including Pinatubo and Krakatoa. Sulfur gas propels the eruptions from Pele, while sulfur dioxide emanates from Prometheus and Loki. New material may emerge through faults on Io's surface. Furthermore, the substance ejected from its volcanic geysers possesses a noteworthy subsequent history. A significant portion returns to the surface, yet some escape and become ionized upon colliding with ions confined within Jupiter's magnetic field. The ionized gas, plasma, constitutes a substantial ring encircling Io, called the plasma torus. Io is the most geologically active entity among the Galilean satellites and the most geologically active body in the solar system. It exhibits significantly greater activity than Earth. Although cartographers have created maps of Io using spacecraft images, these representations are merely transient impressions, as the surface of Io undergoes significant alterations by the time the cartographer finalizes her work, necessitating the creation of a new map. Maps from the Voyager era are as obsolete as yesterday's pizza. Io is marked by black, yellow, red, blue, and brown streaks. These are the specific colors of molecules that contain sulfur. Sulfur is the fundamental element of Io. In a chemistry laboratory, sulfur appears pale yellow. However, that is at ambient temperature. Sulfur-containing organic compounds exhibit colors that vary based on the temperature at which they were synthesized within Io. All large satellites possess tenuous atmospheres, yet Io's atmosphere predominantly comprises sulfur dioxide. A portion of this sulfurous mixture escapes the satellite. Amalthea, a diminutive, proximate Jovian satellite, appears orange. It appears to have been bombarded by Io. Sulfur is an element encountered infrequently. However, a significant portion of Io consists of it, situated above a hypothesized rocky core. Referring to Io as an icy satellite needs to be more accurate. It constitutes a distinct category of entities in its own right. What is the source of energy that drives such endogenic internal behavior? Our selection of energy sources encompasses solar proximity and the thermal energy stored within gas giants. Neither of these applies to Io. It is important to observe that Io is the nearest Galilean satellite to the substantial planet Jupiter. Its orbit exhibits the highest eccentricity among all the Galilean moons. Jupiter's gravitational influence on Io is perpetually fluctuating yet remains significant. Simultaneously, Europa exerts gravitational influence on Io. Sulfur does not exhibit characteristics of a more durable mineral. It is pliable. The fluctuating gravitational forces exert tension and compression on Io, deforming the satellite's internal sulfur like bread dough. Internal friction from the sulfur's self-contact generates heat within the satellite. The energy of Io is derived primarily from Jupiter. It is an energy siphon. Did the Galilean satellites constitute a diminutive replica of the solar system, with Jupiter analogous to the Sun? Jupiter was significantly hotter during the early stages of solar system formation. Did it affect the composition of the Galileans? The densities of the Galilean satellites rise as one approaches Jupiter. A previously hot Jupiter may have vaporized a portion of each satellite's ice, retaining only the rocky and metallic components. Io would serve as the quintessential illustration of this phenomenon, almost ice-free. It is undoubtedly challenging to conceive that the arrangement of satellites, akin to that of the solar system, with rocky terrestrial planets in proximity and icier bodies at a greater distance, is merely coincidental. Jupiter is accompanied by a substantial entourage of smaller satellites alongside the planetary-sized Galileans. The fifth satellite, Amalthea, orbits within Io's vicinity. It was uncovered by E. Barnard, who discovered it in 1892, nearly 3 centuries after Galileo identified the first 4, and it was the final satellite of the solar system to be visually observed. Traditionally, the Jovian satellites were designated using Roman numerals based on their order of discovery. The Galilean moons, Io, Europa, Ganymede, and Kalisto, were labelled as I, Tilati, Tri, and the Ivor, respectively, while Amalthea was V, and Himalaya and Aurora were discovered subsequently. C.D. Perrine of Lick Observatory identified satellites VEs and VE during 1904-05. Official names sanctioned by the International Astronomical Union were established only in 1973. Currently, 67 satellites are acknowledged, predominantly identified through spacecraft imagery, yet only 53 possess sufficiently detailed orbital calculations and designated names. Naming these satellites has proven laborious, and recalling them presents an even greater challenge. Alongside Amalthea, 3 additional inner satellites were identified in Voyager images in 1980. Thebe, which orbits between Amalthea and Io, and Metis and Adrastea, both situated nearer to the planet and, as previously mentioned, delineate the primary Jovian ring, likely replenished by debris from continuous impacts on these satellites. The inner satellites likely originated from the remnants of the protoplanetary disk that enveloped Jupiter during its formation. Amalthea has been photographed by the Voyager spacecraft and observed by the Galileo orbiter. The object is an oblong structure measuring 250 x 146 x 128 kilometers, exhibiting a deep reddish hue, more intense than Mars. This coloration is likely attributed to a layer of sulfur deposited by the continuously active volcanoes of Io. Its density is so low that it is a porous accumulation of debris and ice. It is extensively cratered. A notably large crater measuring 100 km in diameter and 8 km in depth is designated as Pan. The designation Pan is not entirely uncontroversial, as it has also been assigned to a diminutive satellite of Saturn. Himalaya, VI, is the sole other Jovian satellite exceeding 100 km in diameter, making it observable by amateur astronomers with substantial equipment. It is one of 4 satellites between 11,094,000 and 11,737,000 km from Jupiter's center. The remaining moons are Leda, identified by Charles Cowell in 1974, Lysithea, discovered by Seth B. Nicholson in 1938, and Alara, found by Perrine in 1905. Moreover, many outer satellites exist, all diminutive and many exhibiting irregularities, specifically moving in retrograde orbits. These are asteroid-sized entities, each measuring no more than several tens of kilometers in diameter, and were likely captured by Jupiter throughout the extensive history of the solar system. Jupiter's gravity has effectively attracted smaller bodies, as evidenced by its numerous small satellites. It possesses a substantial cohort of short-period comets, characterized by orbital periods under 200 years. These are considered icy bodies captured from the Kuiper belt beyond Neptune. They are categorized into 1. Jupiter family comets, which have periods of less than 20 years, with orbits nearly aligned with the ecliptic and extending little beyond Jupiter. And 2. Halley-type comets, characterized by longer periods and more inclined orbits. The most renowned Jupiter family comet is Encke, with a periodicity of merely 3.3 years. There are numerous others. The most recent tally is approximately 520. Their listing can be found at https://physics.ucf.edu, Y. Fernandez, Comet List, MNL. This is likely an underestimate, as many others have presumably lost their volatiles during multiple approaches to the Sun. Devoid of outgassing or tail formation, they disguise themselves as near-Earth asteroids, identifiable solely by the attributes of their orbits. The Kuiper belt is a predominantly inexhaustible reservoir of these icy proto-cometary entities. It is estimated that, in addition to approximately 100,000 Kuiper belt objects, KBOs, larger than 100 kilometers believed to exist beyond Neptune's orbit, there may be 1 trillion or more comet nuclei-sized objects. For millennia, icy bodies have been dispersing inward from that extensive reservoir toward the Sun, traversing the orbits of the planets and encountering various outcomes, including collisions with Jupiter or its numerous satellites. Due to its mass and extensive gravitational influence, Jupiter and its moons have likely experienced frequent impacts. Consequently, it is not unexpected that the icy surfaces of the outermost Galilean satellite, Kalisto Ganymede, possesses the most heavily cratered surfaces in the solar system. The situation's dynamics and the statistical likelihood of such events occurring intermittently are readily comprehensible. Even with this, as novice amateur astronomers interested in planetary observation, we never anticipated witnessing an impact feature on Jupiter. Ultimately, it was universally acknowledged that Jupiter lacks a solid surface. Subsequently, the notable occurrences of July 1994 transpired. In March 1993, a new comet was identified by the prolific team of Eugene Shoemaker, Carolyn Shoemaker, and David Levy, utilizing the 46-centi Schmidt telescope at Mount Palomar. Their ninth discovery was designated as Shoemaker-Levy 9, SL9. It was promptly recognized as a constituent of the Jupiter family of comets. Thus far, there is nothing atypical regarding any of this. Upon its discovery, SL9 was notably comprised of over 20 fragments, none exceeding 1 kilometer in size, traversing space in a linear formation, commonly termed the string of pearls. Upon analysis, the comet, clearly a mere aggregation of debris, was determined to have disintegrated the preceding July, while passing within a mere 100,000 kilometers of Jupiter's core. This indicated that it had traversed within the orbit of Io, and would have experienced significant tidal stresses from the massive planet. Brian Marsden, affiliated with the Harvard-Smithsonian Center for Astrophysics and serving as the director of the Central Bureau for Astronomical Telegrams, who was then the preeminent authority on the calculations of minor planet and comet orbits, subsequently issued a remarkable telegram. The fragments were traversing a captured orbit around Jupiter and were, in fact, on a direct collision course with the planet. The string of pearls would affect the planet's southern hemisphere in July 1994. Comprehensive calculations indicated that the SL9 fragments would impact the planet's nocturnal hemisphere, approximately at latitude 45 degrees south, with the initial fragment, A, expected to strike on July 16th. This was truly exhilarating. W has been a consistent observer of Jupiter since 1965. S considered the substantial south equatorial belt disturbance of 1975 the most extraordinary phenomenon he had observed. Although the 1975 event was a remarkable instance, similar disturbances had previously transpired and would reoccur. Nevertheless, no one has ever witnessed a comet collide with a planet or the Moon. The gravitational force of Jupiter would propel the comet fragments to a velocity of 60 km/s, 216,000 ton/km/h, resulting in their detonation as 10,000 degrasam fireballs. The collision of the largest fragment would unleash energy equivalent to 600 million megatons of TNT. In contrast, the atomic bombs deployed by the United States on Hiroshima and Nagasaki had yields ranging from 12 to 23 kilotons, whereas the most potent nuclear weapon ever tested, the Tsar bomber of the former Soviet Union, equated to merely 50 megatons of TNT. Evidently, each of the SL9 collisions would generate explosions thousands of times more powerful than the cumulative yield of all nuclear weapons on Earth, and it was anticipated that the resultant shockwave would vaporize both the impactor and portions of Jupiter's atmosphere. Note that Jupiter consistently exhibits minimal phase distortion when observed from Earth. On July 16th, Jupiter was 99% illuminated. The impact sites were located on Jupiter's nocturnal hemisphere, oriented away from Earth. Nevertheless, they swiftly came into sight. At that moment, Jupiter descended shortly after the Sun. It was located 767,137,000 kilometers, or 42.7 light minutes, from Earth. Consequently, any event occurring would require an Earth observer to wait 42.7 minutes post-occurrence to receive information about it. WS commenced a vigil at the eyepiece of his 20-centimeter apochromatic refractor on the afternoon of July 16th, coinciding with the anticipated arrival of Fragment A. The planet was readily observable in the daylight due to its proximity to the Moon. He was immediately astonished to observe an ink-black circular spot, which he initially presumed to be a satellite shadow. Nevertheless, it was more substantial and darker than any satellite shadow he had previously encountered, and upon further examination, it was encircled by an unusual partial ring. The conclusion was unavoidable. Fragment A had arrived and left its imprint. Although WS, unbeknownst to me at that moment, merely 3 hours prior, the Hubble Space Telescope captured a plume of hot gas ascending above the limb immediately following the impact on the planet's night side. TH was also observing Jupiter with colleagues at the University of Rochester Observatory, akin to a busman's holiday. The pearls descended on average every 7 hours, each producing a flash as it was instantaneously incinerated in the planet's stratosphere. Each nightly observation session was anticipated with keen enthusiasm. On July 17th, fragments C, D, and E of the comet descended, leaving conspicuous bruise-like marks similar to those caused by Fragment A. On July 18th, 2 significant fragments, G and H, arrived. Fragment G approached the prior D impact site and generated a plume reaching 3,000 kilometers in height, as the Hubble Space Telescope documented. The resultant dark spot was positioned eccentrically within a dual set of dark rings, formed by a shockwave traveling at 453 ms, half the speed of sound in the Jovian atmosphere. After that, other substantial fragments, designated K and L, made contact the following day. For several nights, the notable G and L spots were present on the disk concurrently, accompanied by their surrounding rings, resembling a pair of large, black, menacing raccoon eyes. By July 22nd, when the final fragment W impacted, the planet at 45 degrees south latitude had been extensively bombarded and encircled by a series of dark, intricate bruises. At times, 6 or 8 spots were observable simultaneously, with the GDS and KW complexes being the most conspicuous, detectable even with a 5-centimeter refractor. These regions, comparable in size to Earth, were the darkest ever observed on Jupiter. Their composition comprised minute particles. Essentially, they were aerosolized remnants of comets re-entering the Jovian stratosphere from the site of the explosions, located approximately 100 to 200 kilometers above the observable cloud layer. Spectroscopic data from the Hubble Space Telescope indicated that only the largest fragments, such as G, successfully penetrated the 2 upper cloud layers, extracting ammonia, sulfur, and hydrogen sulfide. Trace quantities of magnesium, carbon monoxide, and water originating from the comet were also identified. The sequence of bruises designated GS, R, Q, and H was readily observable through small telescopes. Yet the Hubble Space Telescope captured the most exceptional view of these unprecedented events on July 23, 1994. The distinct spots were swiftly disintegrated into tattered remnants by the east-west Jovian winds. Inevitably, they began to diminish until by late September 1994, all that persisted of the colossal wrecks was a diffuse, dark ribbon of material spread throughout the entire impact zone, beneath which the Jovian cloud layers continued to undulate like a sea with indifferent complacency. WS continued his observations until May 1995. By that time, the polar region above 45 degrees latitude still exhibited a slate-grey or charcoal hue, presumably due to an amalgamation of soot from the fragmented comets. The consequences of the SL9 crashes were relatively insignificant and ephemeral. One can only contemplate the devastation if the same fragments had collided with the Earth. Such an occurrence would have signified the extinction of humanity and potentially all life. Those who observed these significant events felt fortunate to witness a phenomenon of cosmic importance. Akin to observing, from a secure distance, the Kt asteroid impact that potentially eradicated the dinosaurs 65 million years ago. The frequency with which substantial objects, such as the SL9 fragments, may impact Jupiter remains indeterminate. Current estimates suggest that the diameter of SL9 before its disintegration was approximately 1.5 kilometers, with the largest fragments measuring between 500 and 700 meters in width. Eugene Shoemaker proposed that a body 1.5 kilometers in diameter could impact Jupiter approximately once every century, whereas collisions with previously fragmented comets, such as SL9, would likely occur at least 20 times less often. David Kari, University of California, Santa Barbara, and Luke Dons, NASA Ames Research Center, conducted a quantitative analysis utilizing a computer simulation that tracked 50,000 Jupiter family comets over 100,000 years. They recorded 750 simulated impacts, including 166 from captured comets and 1,052 disruptions within the Roche zone, defined as the radius at which solid bodies would be disintegrated by Jupiter's tidal forces. They also observed thousands of captures. In their simulation, only 2 instances were observed in which a captured comet was disrupted and subsequently impacted on its next orbit, akin to SL9. This mechanism is the sole means of producing a series of impacts, as the fragments would become too dispersed after an additional orbit to achieve this effect. Consequently, their optimal estimations for the mean intervals of 1-kilometer objects, such as fragment G, indicated impacts occurring every 240 years, disruptions every 170 years, and SL9 string-of-pearl type impacts every 90,000 years. While these occurrences may be infrequent in daily life, indicating our exceptional fortune in witnessing them, they are not uncommon over geological timescales, as analogous comet disruption events have impacted the Moon. The most renowned instance is the crater chain located on the floor of Davy, a crater situated on the northeastern edge of Mare Nubium. At least 8 chains have been discovered on Kalisto's damaged surface. Following the SL9 impacts, the archives were plundered for records of solitary comet impacts concealed within the myriad of planetary observations. Such events necessitate additional effort to analyze records of typical dark cloud characteristics. To assist in this endeavor, co-author T.H. suggested a set of pertinent criteria. Typically, Jovian cloud formations exhibit the most pronounced contrast at the central meridian. As they rotate towards the limb, the augmented mass of superimposed hazes in our line of sight diminishes contrast, causing the spots to vanish before crossing the limb or terminator, the day-night boundary. This did not apply to the SL9 locations. The substance in the SL9 locations was deposited in the Jovian stratosphere. An augmented mass of spot material in the line of sight at the limb resulted in limb darkening. The sole Jovian characteristic lacking relative limb brightening is a satellite shadow, which exhibits uniform contrast during its transit across the planet. Thus far, the characteristics in the planet's archival records still need to meet these criteria. However, this is merely to be anticipated. Until the latter half of the 19th century, few individuals observed Jupiter, and their telescopes were diminutive, with a few notable exceptions. The 20th century marked the pinnacle of traditional film, silver halide photography, for which Jupiter, due to forthcoming explanations, is an inappropriate subject. It was only with the emergence of webcams and video imaging, utilized by numerous skilled and dedicated observers globally, that there was a plausible opportunity for an impact to be documented, and as we will demonstrate, this has indeed occurred. As of today, amateur observers of Jupiter have documented a minimum of 4 individual impacts since SL9. Anthony Wesley recorded the initial observation at midnight on July 19, 2009, utilizing his 36-centimeter reflector at his observatory near Murrumbateman, Australia. Disheartened by the observing conditions, atmospheric instability distorting the telescopic image, and on the verge of concluding his session, Wesley reconsidered just before selecting exit on his computer. He opted to wait for 30 minutes to ascertain whether conditions would ameliorate. Upon returning to the telescope, he observed a faint black spot near the eastern limb in the South Polar region that had not existed during imaging of the same area 2 days prior. Once he assured himself that he was not dreaming and that the phenomenon was genuine, Wesley dispatched email notifications to fellow astronomers, including Glenn Orton, who, 20 hours later, utilized NASA's infrared telescope facility on Mauna Kea, Hawaii, to verify that it was indeed an impact. Astronomers utilized the Keck, Gemini North, Very Large Telescope, and Hubble Space Telescope to observe the feature's evolution over several weeks. By calculating the object's trajectory, they determined it was more likely rocky than icy, indicating it was an asteroid rather than a comet-like SL9. Nearly a year later, during a visit to a friend in Broken, Australia, Wesley captured a video of Jupiter and recorded another impact, this time as a flash, on June 6, 2010. Christopher Go also documented it in the Philippines. The event was significantly smaller than the one in 2009, leaving no impact. On September 10, 2012, Dan Peterson documented another flash event in Racine, Wisconsin, while visually observing Jupiter through a Meade 30cm Schmidt-Cassegrain telescope. This constituted the inaugural visual observation of a Jovian impact fireball. Peterson contacted Kyle Cudworth at the adjacent Yerkes Observatory via telephone and emailed Jupiter observers Richard Schmude of ALPO, John Rogers of the BAA, and Christopher Go. He also published a thread on the website Cloudy Nights, in which he declared, "I observed an explosion on Jupiter this morning." George Hall, who recorded a video of Jupiter that morning, was among those who observed Peterson's thread. Hall inadvertently captured Peterson's flash in 22 frames while examining his video clip. The most recent fireball lasted approximately 1 second and was observed on Jupiter's limb on March 17, 2016, by video imagers Gerrit Kernbauer in Australia and John McKeon in Ireland. Undoubtedly, these occurrences are more prevalent than previously assumed, and documenting effects on Jupiter represents a domain where amateurs can still contribute significant findings. A coordinated global initiative predominantly involving amateur astronomers indicates that yearly, as many as 6.5 observable impact events may transpire on Jupiter. The recorded instances have pertained to minor asteroids or comets measuring approximately 10 meters, equivalent in energy to the smallest fragments of comet SL9 or the Chelyabinsk meteoroid. This near-Earth asteroid generated a significant fireball over the southern Urals in 2013. These objects detonate above Jupiter's cloud layers, leaving no remnants within the clouds, unlike the substantial S9 fragments. The most recent spacecraft to investigate Jupiter was launched from Cape Canaveral, Florida on August 5, 2011. Juno, named after Jupiter's envious consort, who could penetrate the clouds he shrouded himself in to discern his true form, traveled rapidly to the distant planet, facilitated by an Earth flyby that harnessed some of our planet's gravitational potential energy. It entered Jovian space on June 24, 2016, traversing the bow shock, the point at which Jupiter's magnetic field surpasses that of the Sun, and on July 4, 2016, became the second spacecraft, following Galileo, to achieve orbit around the gas giant. The inaugural Jupiter orbiter Galileo was launched from a space shuttle on October 18, 1989. Following gravitational assist flybys of Venus and Earth, it reached Jupiter and entered an equatorial orbit around the planet on September 7, 1995. It remained in orbit around Jupiter until September 23, 2003, when it was directed on a collision trajectory with Jupiter to prevent a potential collision and possible biological contamination of one of the Jovian moons. Unlike Galileo, which utilized a radioactive energy source, Juno is exclusively powered by solar energy. In contrast to Galileo, which maintained a near-equatorial orbit, Juno was deployed into a polar orbit around Jupiter, providing scientists with the first detailed images of Jupiter's poles. After a 53-day extended orbit around Jupiter, it executed its initial close approach to the planet, 4,200 kilometers from the cloud tops, on August 27, 2016. Initially, mission planners aimed to activate the primary engine and place Juno into a 14-day orbit. However, upon receiving telemetry suggesting potential issues with essential valves in the propulsion system, a conservative decision was made to maintain Juno's original orbit. Although completing the mission objectives will require additional time, scientists are assured of their success. At the time of writing, May 2017, Juno has recently accomplished its 6th of 37 flybys. Upon the mission's conclusion in July 2018, Juno will be deliberately deorbited into Jupiter, similar to the Galileo spacecraft, as a precautionary measure to mitigate any potential risk of biological contamination of the planet's moons. Although the mission remains nascent, it has already yielded significant findings, including the inaugural detailed observations of the planet's polar regions. Pioneer 11 was the only other spacecraft to capture non-oblique images of the planet's poles in 1974, albeit from a distance 10 times greater and utilizing a significantly more rudimentary imaging system. Earth-based observations had already established that within 30 degrees of latitude from each pole, where the zonal winds of lower latitudes diminish, the familiar zonal banded structure disintegrates, yielding a dusky blue-gray polar region. Juno reveals this region to be considerably bluer and more tempestuous than previously conceived. The most prominent features are bright ovals with spiral extensions, which time-lapse image sequences indicate are cyclones, rotating counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Several of these cyclones congregate near each pole. Other luminous areas are unremarkable and resemble the minor chaotic characteristics observed in Voyager images of low-latitude clouds. A collection of white ovals congregates near the poles in both hemispheres, although the configurations at each pole are distinctly different. It remains unclear whether these features are in stable equilibrium or are dynamic and subject to evolution over time. Another significant finding from Juno is that the circumpolar waves on Jupiter do not produce a north polar hexagon as observed on Saturn, demonstrating that the polar dynamics and atmospheric structures of these planets are fundamentally different. A significant outcome was a high-altitude cloud, potentially a detached haze layer, projected shadows onto the primary polar cloud deck 60 kilometers beneath. Neptune is the only planet where this phenomenon has been observed. Where Voyager 2 documented shadows cast by high-altitude cirrus clouds of methane ice onto the underlying bluish methane clouds during its August 1989 flyby. The Juno spacecraft captured images using the visible light Juno CAM instrument, which employs blue, green, red, and methane filters, alongside thermal emission data from its microwave radiometer and Jovian infrared auroral mapper, revealing previously unexplored areas of Jupiter's deep atmosphere. Before Juno, most knowledge regarding Jupiter's atmosphere was derived from observations of the upper cloud layers, specifically regions with pressures of 0.5 bar or lower. Notably, there was a singular series of measurements extending to the 22 bar level at one location on the planet, obtained by the Galileo probe, but this constituted the extent of the data available. It was presumed that Jupiter's appearance remained consistent beneath the cloud tops in its sunless depths. However, no evidence supported this claim. Although Juno is still in the early stages of its mission, it has demonstrated that the situation is considerably more intricate beneath the cloud layers. The primary characteristic is the equatorial plume and the adjacent nebula, which, at least to the 60 bar pressure level, resemble a system akin to the Hadley cell on Earth, where air ascends near the equator, moves poleward, descends at approximately 30-degree latitude north or south, and subsequently returns equatorward near the surface. The Hadley cell on Earth accounts for the tropical trade winds. A comparable mechanism has been hypothesized to elucidate Jupiter's low-latitude circulation. However, the dynamics differ in that context. On Jupiter, ammonia serves a function analogous to water on Earth. Ammonia ascending in the equatorial plume crystallizes, yet the precipitated crystals evaporate at the 1.5 bar pressure level, resulting in a Hadley cell system devoid of precipitation. The GIRAM instrument also supplied data regarding regions where thermal radiation emanates from pressures exceeding a few bars, The hot spots, indicative of areas of downwelling and arid air, where relative humidity is below 3%, primarily encompass the region between 5 degrees and 20 degrees within the Nebular and other principal belts. The latitudes are clearly cooler, more humid areas distinguished by upwelling. The great red spot and white ovals are regions of upwelling. Juno's findings indicate that Jupiter's belts and zones possess substantial depths, extending hundreds of kilometers below the surface, rather than merely existing as superficial layers. Another significant finding from Juno's magnetometer investigation is that the planet's magnetic field, already recognized as the most intense planetary magnetic field in the solar system, was nearly twice as strong as anticipated. Consequently, the electrically conductive fluid in convective motion that creates the dynamo responsible for generating the magnetic field must reside in a region not far beneath the surface, an unforeseen outcome. The most plausible explanation is that it transpires in a molecular hydrogen layer above the area where escalating pressure in the Jovian depths triggers a transition to metallic hydrogen. Juno has conducted numerous observations of the Jovian aurorae from its polar orbit, revealing distinct processes compared to Earth's aurorae. These intriguing details and Juno's preliminary findings have already transformed our understanding of Jovian conditions and initiated responses to several significant inquiries. By the conclusion of the mission in July 2018, it is anticipated that we will possess, at minimum, provisional responses to the following inquiries. What is the actual quantity of water present on Jupiter? Understanding this will assist in evaluating competing theories regarding Jupiter's formation. Did the hydrogen-helium Jupiter form simultaneously? Was it gathered by a pre-existing core? What was the significance of icy planetesimal impacts in delivering water to Jupiter and the primordial Earth? 2. What is Jupiter's deep atmosphere's composition, temperature, and cloud dynamics? In contrast to Earth, Jupiter remains in a primordial condition. What do Jupiter's current depths reveal about our planet's primordial history? 3. What is the comprehensive configuration of Jupiter's magnetic field? Regarding its gravitational field? Mapping these structures will yield improved models of the Jovian interior, including determining whether the core is solid, liquid, or composed of both layers. We would also like to ascertain the dimensions of the core and its composition. 4. What is the behavior of Jupiter's magnetosphere? How does it capture and direct charged particles into the upper atmosphere that produce the polar aurora, the most magnificent solar system? Juno's highly elliptical polar orbit renders it unsuitable for examining the equatorial Jovian moons. Additional missions are scheduled for that exploration, including the European Space Agency's Jupiter Icy Moons Explorer JUICE, launched in 2022 and expected to arrive in orbit around Ganymede in 2030. The mission of JUICE is to enhance our comprehension of the conditions necessary for planet formation and potentially the origins of life. NASA has prioritized its mission to Europa, the satellite most likely to support life, with a proposed launch date in the late 2020s. These plans are exhilarating. However, we must acknowledge the missions that preceded them. Cassini and Juno accomplished what once appeared inconceivable by entering orbit around the most majestic planets. Preceding them were the Pioneer and Voyager flyby missions. The Pioneers, equipped with a plaque designed by Carl Sagan and his colleagues to convey information about Earth and its inhabitants, encountered Jupiter while departing the solar system. The Voyagers carried a phonograph record featuring sounds and music from Earth. Indeed, the enormity of space renders it improbable for any intelligent extraterrestrial civilization to encounter these artifacts, just as the likelihood of us detecting any scent from an extrasolar planet is nearly non-existent. Pioneer 10's final transmission was received on January 22, 2003, from beyond Neptune, while a notable event for Voyager transpired on August 25, 2012, when Voyager 1 officially crossed the heliopause and entered interstellar space. As our flyby probes progress, they have ceased to traverse the planets of our system and now venture into the domain of distant stars, Numerous entities possess planets, a fact unknown at the time of their departure. Over 2,000 are already identified, and their total must ultimately be incalculable. Numerous initial discoveries, unexpected by astronomers, are high-mass exoplanets that orbit closely to their host stars, less than 0.5 astronomical units, where 1 astronomical unit is the distance from the Earth to the Sun. These are commonly known as hot Jupiters. These planets possess atmospheric temperatures reaching thousands of degrees Celsius, indicating they could not have originated in their current positions. Clearly, they have relocated within their systems, akin to the migration believed to have occurred among Jupiter and the other gas giants during the solar system's early history. Jupiter and its 4 prominent moons are gratifying subjects, even when observed through binoculars. The moons undergo a constant transformation in their perpetual movement, evoking reflections on Galileo's achievements and tribulations. Due to Jupiter's substantial apparent diameter, the intervals suitable for profitable observation, and the continuous intrigue of its diverse and dynamic phenomena, the planet persists as the amateur's planet, even in the era of Galileo and Juno. An interested and motivated individual can still make valuable contributions to the esteemed observing programs of the Jupiter sections of the BAA and ALPO, particularly if equipped with video and CCD imaging technology, enabling data acquisition with enduring scientific significance. It is important to note that Stanley Williams and Elmer J. Rees, prominent figures among planetary students, conducted most of their notable work using reflectors with apertures smaller than 20 centimeters. In March 1978, one of the authors, W.S., independently discovered a new SEB disturbance using a 20 centimeter reflector at home from college. The accomplishment was unremarkable. It merely involved observing at the appropriate moment and possessing sufficient knowledge to comprehend the importance of the observation. Initially, students aspiring to undertake rigorous study should allocate time to familiarize themselves with the belts and zones nomenclature and abbreviations. The features depicted in the diagram illustrate the average appearance, and given that Jupiter is a planet characterized by cloud formations that frequently experience rapid and dramatic alterations, actual observations will reveal considerable deviations from the average. The belts and zones are discernible even through diminutive telescopes. Greater apertures reveal significant non-uniformity. The edges of the belts appear distinctly frayed, with the interiors frequently excavated. Certain features are commonly designated as spots. However, more descriptive terminology initially introduced by classical observers in planetary literature may be advantageous in specific instances. For instance, dark and light features along the edges of the belts are often termed dark projections and light bays. The projections can be short, stubby, or elongated into streaks or wisps. If distinctly curved, these streaks are referred to as festoons. A festoon with a bright white spot at its base is identified as a plume. Short, dark streaks, typically brownish, are referred to as barges. Large, elongated spots are designated as ovals, among other terms. Although these terms offer convenient shorthand descriptions, they are typically semi-official. Furthermore, they, particularly in the case of barges, do not suggest any assumptions regarding the nature of these features. Though much of the amateur monitoring of Jupiter is now done with CCDs, avid visual observers of the planet still exist and do useful work. Most observers will want to attempt a few whole disk sketches to record a given apparition's overall appearance. A prepared disk giving the planet's oblate outline dimensions will be convenient, such as the one provided overleaf that is suitable for copying. If recent measurements of the latitudes of the belts are in hand, it may be convenient to sketch the belt's positions lightly before venturing to the telescope. Unless there is a compelling reason to do otherwise, it is best to study the planet for half an hour or so before beginning a sketch of the seeing, that is, the quality of atmospheric conditions. Unless the air is steady and the definition good, there is not much point in proceeding further. This will also allow the positions and forms of the most conspicuous markings to be laid down. Once a sketch is begun, It is necessary, of course, owing to the rapidity of Jupiter's rotation, to put in the main features quickly. But once these have been established, the finer features can be entered concerning the main features and at greater leisure. Rather than full disk representations, it is generally more advantageous to create detailed sketches of notable planetary regions or strip maps that illustrate features observed over several hours at the eyepiece. Recent years have highlighted prominent features such as the diminishing Great Red Spot and/or the Red Spot Hollow, the white ovals in their various interactions and mergers, and the dark projections of the nebula. Observers should particularly monitor significant disturbances that occur every few years, including the fading of the Seb followed by a dramatic revival. The NTB revivals and the broadening cycles of the nebula previously discussed are also noteworthy. Determining spot or feature longitudes aids in identifying currents. Timings are particularly beneficial when supplemented with sketches of the features being timed. Consistent with practices established since Stanley Williams's era, longitude determinations require estimating transits across the central meridian, chem. Accuracy to the nearest minute is adequate, equating to merely 0.6 degrees of longitudinal rotation. The longitude must subsequently be computed in System 1 or 2. Due to its low surface brightness and pronounced limb darkness, Jupiter has never been an ideal subject for conventional silver halide photography. Consequently, even in the photographic era, superior work persisted through visual techniques. Nonetheless, emerging technology has instigated a revolution. During the early 21st century, enthusiasts employed webcams and image processing software to choose and compile the clearest images. Planetary cameras, derived from original webcam technology, are specifically engineered for digital planetary observations, capable of recording videos with hundreds of images at a rate of 15 to 200 frames per second. Subsequently processed with software like RegiStax or AutoStackit. The images containing the highest spatial frequency components are aligned and stacked before additional image processing. This has evolved into a highly specialized domain, and regrettably, a more detailed discussion is beyond the purview of the current work. A variety of reference materials are accessible. Numerous amateurs have excelled in this endeavor. Donald C. Parker, who passed away, is noteworthy as a pioneer of Jupiter CCD imaging from Coral Gables, Florida. Leo Aerts from Belgium and Damien Peach from England are regarded as exceptional imagers presently engaged in their field. The opportunities for the proficient amateur equipped with a modest telescope and CCD technology are limitless. Amateurs globally can now observe alterations in the structure and development of atmospheric phenomena on the gas giant daily, except when the planet is obscured by the sun and thus rendered invisible. They offer an uninterrupted account of the extensive climatic cycles on Jupiter and provide extensive geographical coverage of events, which is essential due to Jupiter's rapid rotation. Scientific astronomers consistently observe Jupiter through long-term monitoring programs, with occasional observations conducted using the Hubble Space Telescope. However, these observations are sporadic. Furthermore, most professional research has been performed in the infrared, IR spectrum. Amateurs can image in the red, 580-670 nm, green, 500-580 nm, and blue, 390-500 nm, thereby offering multi-wavelength coverage. Furthermore, an increasing number of amateurs are utilizing IR filters, 680-900 nm, which allow for marginally greater penetration into the Jovian clouds. The narrow-band methane filter, 890 nm, which reveals light reflected from the uppermost clouds, and near-ultraviolet filters, below 390 or 360 nm contingent on the manufacturer. Due to the unpredictable nature of certain intriguing Jovian phenomena, amateurs typically serve as the initial observers. This is particularly applicable to impact events, all of which, except for the SL9 impacts 1994, have been identified by amateurs. Despite Juno's current orbit around Jupiter, amateur astronomers will remain essential. In the initial decades of the 21st century, the magnificent planet continues to be the domain of amateurs. Despite being an ancient planet, having formed approximately 4.6 billion years ago alongside the Sun, it has maintained its dominant position in the solar system ever since. It remains eternally youthful and as pristine as each evening's observation. It will persist into the future to benefit the student equipped with a small telescope engaged in visual or CCD observations. The rewards will generally correlate with the time invested, effort exerted, and skills cultivated through practice and application.